Let's get started with tutorial on convex duality by Thomas. So Thomas received his PhD at TU Munich in 2020, and since then has been here at RIKEN for 3 years as a postdoc, and then since 2023 as a tenured research scientist. And he focuses on optimization and Bayesian deep learning, and his research has also been awarded several times.
Yeah, thank you very much. So yeah, I will give a short tutorial today on convex duality. And yeah, I mean, the name of this workshop is Bayes-Duality Workshop, and probably most of you don't know what we mean by Bayes-Duality. And so maybe we are also not so sure ourselves, but I guess we know very well what is convex duality, so maybe yeah, I will give a tutorial on this, and then we can see how to go from there. Yeah, so I hope, I mean, I don't have that many slides, so I hope that this can be more interactive and you can ask many questions. Everything you always wanted to know about convexity or duality, just ask it. Otherwise, I think I might finish quite early otherwise. But yeah, I mean, we can also have a longer lunch break if that's the case. So yeah, so this is the overview for today's talk. I will start, we can start with a discussion. So what is this duality? What does it even mean? I think yesterday we didn't have that much, but in Alex Immer's talk, I mean, there was a really nice example on duality that was actually useful in computation. So what we can maybe first have a discussion about this. Then I will show some motivating examples of duality in machine learning. Well, yesterday we saw a nice one, but I will show maybe very classical ones from long ago. And at the end, I will do a more in-depth tutorial on the basics of convex duality, where we really do some concrete calculations and so on. Yeah, so maybe to start with, what is duality? You can just, if something comes to your mind, I mean, people who attended this last year, then please be quiet, but yeah, just what comes to your mind, feel free to say something. Transpose of a matrix. I think that's a very good example, I think, of duality between linear spaces. You have a vector space, you have a dual vector space. It's a very specific thing, right? It's like an example, but what is duality in general? What does it mean? Okay, so there's two things that come in a pair, and then if I change one thing, the other, they're somehow connected, and if I change one thing, the other one changes. Okay. Yes? Yeah, very good. I think it's much better than last year. Because last year people were saying, oh, KKT conditions or Lagrange multipliers or things like this. But this is typically if I at the machine learning conference or if people from optimization are coming, they really very specifically think that duality is related to optimization and Lagrange multipliers and so on. And but I hope to convince you here in this introduction that this is like a more general concept, and that we should be a bit open-minded. Conjugation, yeah. I see. Mm-hmm. Yeah, one more comment here. Okay, yeah, that's all very good. So I actually also didn't know, or well, you guys know actually, but I didn't really know what's duality, so I just Googled it. And I found this really nice paper by Michael Atiyah. So he was a famous mathematician. I think he won the Fields Medal also. And he wrote this really beautiful paper called Duality in Mathematics and Physics, which are much more mature disciplines maybe than machine learning. And maybe I'll just read it because it's so well written. So in the abstract he says, duality is one of the oldest and most fruitful ideas in mathematics. And then in the introduction he says, duality in mathematics is not a theorem. So it's not like some theorem like KKT conditions or something like that, but it's a principle. And it has a very simple origin. It's very powerful and useful. So we've seen this yesterday, and Alex used it to really do some computational things. And it has also a very long history going back hundreds of years. And over time it has been adapted and modified, so we can still use it in novel situations. And in mathematics and physics, it's very mature, so it appears in many subjects in mathematics, geometry, algebra analysis, and also in physics. And fundamentally, duality gives two different points of view of looking at the same object. There are many things that have two different points of view, and in principle, they are all dualities. So that's his definition of duality, and I think it's quite nice and open-minded that we can call many things duality, and it doesn't have to be so restricted to maybe optimization viewpoints. And just as a general feeling that if you read this full paper, he will describe many dualities used in mathematics and physics, and I don't know almost any of them. So that just gave me the feeling that in mathematics this is very deeply developed, and maybe in machine learning we haven't found many useful dualities yet. And most of the dualities that we actually use in practice are either the one from linear algebra with the transpose, or maybe the convex duality that I will talk about. But just as a thought-provoking idea that there can be many more, and I think that was maybe also the spirit with our Bayes-Duality project, that maybe there's some duality lurking behind Bayes, and we can maybe uncover something there. It's still work in progress. Okay, so we were organizing also a workshop at ICML 2023, which we fittingly called Duality Principles. As Atiyah said, duality is not a theorem, but it's a principle. So we were organizing last year this workshop on duality principles for modern machine learning, together with Zelda, who's also here somewhere. Yeah, she's sitting over there. And I think she will also give a talk on the last day, maybe, on some uses of duality. And also Mathieu Bordel and Emti. So the idea was somehow of this workshop was to bring together researchers who work on various duality concepts from different fields to see whether we can bring researchers together and advance this. And here we listed like the currently used ones in machine learning. It's like fancy duality and convex optimization, which is what I will talk today about. But there's also this representer theorem in kernel methods, and also for Bayes. There's dually flat spaces in information geometry. So we had some information geometry people at this workshop. So we hope to revive the interest of the community in these duality principles. And maybe next ICML we will look into organizing another of these. This year we have this workshop, so we didn't organize it this year. But the workshop was a big success. So there were actually surprisingly many people joining us, and we had a fun time in Hawaii. And this was after the workshop. We grabbed some drinks afterwards, and I think there were over 100 people joining the actual workshop, which was surprising because in the end it's a kind of a niche topic, very theoretical topic, and it got a broad. There were many people joining us. So yeah, so maybe we discussed now what is duality, and to motivate you further, maybe we can look at some examples of duality in machine learning. So the first example where I personally encountered duality is in the context of image processing. So in the previous life, I worked on image processing problems, and there's a very popular model which is called the total variation smoothing model. And I will motivate on this example a bit how duality is useful there. So this is a kind of an image processing problem where we have a graph, and our variable u is basically on the vertices of the graph. So for every vertex in the graph, we have some optimization variable, and this first term is some kind of data fitting term. So this input image that you see here with the lighthouse, that's f, and then we say, okay, every node on this graph, it should be close to f. And if we would just minimize this first term here, our solution u, it would just give us back the input image. Then there's here this extra term which says, okay, two neighboring vertices, they should have the same value, and they are penalized with this absolute value. It's basically saying the absolute value of the neighbors along the edges should be small as well, and this gives you a smoothing of this image. So if you solve that optimization problem, you will get basically a smooth version of your input. So what does this have to do with duality? One big reason people like duality in machine learning is to deal with non-differentiable problems. So we have here the absolute value function, which looks like this. And at 0, this is non-differentiable. And if you try to solve that with gradient descent, you will run into some problems, right? Because you have this kink, you will keep bouncing around if your step size is constant. So you will never find the minimum unless you anneal the step size to 0. There's a common question.
All I find is kind of say the problem is only one point. You know? I think the deeper problem is that the Hessian is 0. I think that's the problem, not that you cannot differentiate it at 0. So the absolute value, you know, that's not the point. That measures 0. You know?
Yeah.
So I think the underlying problem that is that locally there is no information about the Hessian.
There's no.
I think that's the real problem. Whatever, because you can always do epsilon stuff. You can play the epsilon game at 0, and your problems will still remain.
It's a very good comment. So you're talking about the Hessian, but already if you look at the gradient, it's basically a step function. And there's no information you're here. You don't know how far you should go because there's no curvature. So you're completely lost. So this is a hard problem to solve. Even if you, yeah, it's a very good comment. Even if you smooth it a little bit at 0, it will still be hard to optimize.
It's not the non-differentiability. For this, they cannot be the same. You can phrase it, but I think the deeper problem is that.
This is exactly true.
Yeah.
This is, I completely agree.
I've seen this so many times, but I think this comment is confusing.
Yes. Okay, sorry. I also think it's confusing actually, so maybe we cross this out, but it's more, this function is more, let's say, there's no much local information, doesn't give you anything about the global shape of the function. But people have used duality to simplify that problem. So let's see how this was done. So convex duality to the rescue. Or maybe the hard problem doesn't go away, but at least duality can help you to design new algorithms for this problem that are maybe better than just running gradient descent on this energy. So, okay, we can rewrite it a little bit. This is just introducing some notation. This is equivalent. We have some matrix D, which maps from the vertices to the edges. And then we have one big L1 norm, which sums up these absolute value functions. And then it turns out, at the end of the tutorial, you will know how this is done. But you can suddenly come up with a completely different optimization problem, which is now on the edges. So my variable P, suddenly now on the edges of the image rather than on the vertices. And the cost function has completely changed. It's now differentiable. And we have some constraint on our p variable. There's a completely different optimization problem suddenly. And then there's if I solve one of them, I have solved the other one. So these are two different things which are connected through this equation. So if I compute the solution to the lower problem, I can recover the solution of the upper problem. And this can help me, for example, to design new algorithms, because suddenly I have this problem which I can now maybe solve with gradient descent because the cost function is differentiable. And then once I've solved it, I just use this equation and I get a solution to the upper problem. And yeah, so this is smooth, so this is good. And if you run gradient descent on this problem, of course, you have to project back on the feasible set in every iteration. Antonin Chambol did this method in 2004. He proposed this, and he called it an algorithm for total variation minimization in applications. And this is a very popular method because with constant step size, you can converge the solution. So this is one reason duality is very liked in machine learning, because you can find an alternative way of solving your problem. And then maybe this alternative way is amenable to some other algorithms. And you can also see that the dimension of the dual problem is different than the dimension of the primal problem. We have also seen this yesterday in Alex's talk. So here the primal variable is the number of vertices, the dual is the number of edges. So maybe one problem is more low dimensional than the other one. So it can also be beneficial. Like yesterday we've seen it's the number of data examples versus number of parameters. And so this is very useful. So that's why people like this convex duality. And maybe at the end of the tutorial, you will perfectly understand how we went from one problem to the other problem. Yeah, there's a question. Yeah, it's a good question whether one should call this a reparameterization. Yeah, it's a reparameterization. In some sense, it's a reparameterization. So it turns out that this is somehow you're working in the space of gradients. So you will see this later. So it can somehow be understood as a reparameterization. And there's actually many reparameterizations. There's many ways to reparameterize your problem. This is a very specific one. But yeah, it's true, I think. You will learn it soon. And if you don't learn it, then ask. Yeah. I mean, it's in some sense a loose way of, I mean, it's not directly.
Because you can transform the solution in one space to the other.
Yes, in some sense.
If you have P star, you can get U star. Not the other way around.
Yes, I mean, this only holds at the optimum. Yeah. So usually, typically, if you say you do a reparameterization, you introduce some U tilde, some f of u or something, and then you can plug it in. Like you know, u is f minus 1 of u tilde. And this is the classic reparameterization. But I think this convex is slightly different, I would say. It's slightly different, but if you, yeah, it's not directly a reparameterization like this, I think. Only at the optimum you have some kind of relation like this. Yes, so for the reparameterization, you need maybe some kind of invertible map. And as Yusong pointed out, here these spaces have different dimensions, and then there's a mathematician here, so I'm scared, but maybe between two spaces, at least if the dimension is the same, then maybe there's no, if the dimension between two spaces is different, then maybe there's no diffeomorphism, at least. So, yes, but yeah, there's space filling curves and so on, but let's not get into this. Okay. Okay, there's one more question.
I found this interesting that like graphs by themselves are independent duality between vertices and faces. And in this case, we went from vertices to edges. But how did the optimization sectors know about the edges? Is it because of D?
Yes. D is a map from the vertices to the edges. It basically computes the derivative. Like you take the difference between two neighboring guys and then you're on the edge. That's how, so the dual is always in that edge space because of this D matrix. And I think this phase vertex duality, that's more for simplicial complexes over there. For the graph, you just have vertices and edges, right? For general graph, you don't even always have phases, I think. I don't know. Yeah, for the grid, you have phases. So one other reason why we are really excited about duality is these dual variables, they encode very interesting information about your solution. So what I did here is on the left, we see the solution of the primal problem, but on the right-hand side, I plotted the solution of the dual problem. And we can see that the dual variables are large at the edges, where there's a big change. So the lighthouse here is black, and then the sky is blue. And then at this point, the dual variable is very large. And what you will also learn today is that the magnitude of the dual variable will tell you how much your optimal value will change if you perturb the data of the problem. So let's say I would remove that edge here, because this is kind of a piecewise constant segmentation of my image. If I would remove that edge here, then maybe these regions would merge, and then my optimal value function would change a lot. And these dual variables, they encode places in the image where if you would modify that image at these places, you would get a huge change in your minimum value. So with this Bayes-Duality, we are hoping to really use these dual variables to understand our solutions. So we've trained a neural network on some data, and then why is the neural network stable? If I perturb that weight a little bit, will the solution change a lot? Or if I remove that data point, what would happen? And then for a good model, it's somehow robust. So it's not so sensitive to, like, let's say I give you a neural net and I change one weight just a little bit, and suddenly it completely changes its predictions. It's a really bad model. We don't want to have something that's so sensitive. So the hope is with this duality, we can get some understanding on sensitivities also. And yeah, I will at the end comment on the exact mathematical reason why this looks like this. Yeah, so here's now another example. Maybe we go away from total variation image smoothing to machine learning. So I have this 2 moons data set, and I trained a linear model on that data set with some feature map, and I got this green line. So I have this model now, and then let's say I remove some data points. I randomly removed some data points, and then I retrained that model, and I get this black curve. Or I remove some other data points, I get the other black curve. Then I'm very smart, and I remove just the right data points, and suddenly I get exactly the same solution. How can this be possible? How was I able to do this? And the answer also lies in duality. So let's look at this. So how was I able to find these points that I can remove to get the same solution? So this is the classical empirical risk minimization problem. If our data points X, our labels Y, L2 regularization. So I minimize this to find this linear model. And just by taking the derivative and setting it to 0, we can see that the solution satisfies the following equation. We get here theta star. That's the derivative of this guy. So the derivative of this guy is delta times theta, and I put the delta on the other side. So I divide it by delta. So this theta star comes from the derivative of this one. And then I take the derivative of this, which is L prime of what's inside. And I have to use the chain rule. I differentiate this guy, I get xi, and I have the sum. So we know that our optimal solution is actually composed as the sum of many derivatives times the data points. So this is some kind of, people call it representer theorem, that the optimal solution is given as a sum of the data points. And then if we call these derivatives here L prime, if we just call them alpha, or -1 over delta times L prime, we call it alpha. We have this nice equation that theta star is the sum of all these alphas times x. And what I simply did is, I removed all the data points where alpha I star almost equals 0. And then, because we know that these data points don't affect my optimal solution, because I multiply them with 0, so they don't affect my theta star, so I can just remove them and nothing happens to my optimal solution, because the optimal solution is unique. This is a convex problem. So this is very important, that we have here uniqueness. So if it's like deep learning, you cannot do this because you will have multiple solutions and then these variables will be different so it's not so easy to do it, but in this convex problem, you can simply remove these data points and then nothing changes. Yeah, so this is what happened. I hope this was clear, completely clear. Sorry? Is there a link with core sets? Well, I mean, so people typically, yeah, thank you, please help me actually. So what people call these points, they call it support vectors. So what I used here is I used the hinge loss. And then this is equivalent to training a support vector machine. And these points, people usually call them support vectors, but on core sets, I mean, I don't know really the definition of core sets, but.
There's no definition.
Okay.
Something.
There is a definition.
Representation, there is one. But the concept.
Yeah, everything has a concept. You're right. It's the same.
So I think it's also
Yeah. Epsilon approximation. Yes, this is for sure. You can study these things. Like, I think you can, if you also start removing alphas which are not completely 0, I think you can analyze the epsilon and so on. This should be very classical. Like, this is, I mean, probably people did this 20 or 30 years ago for support vector machines, these things. I think Eugene here was also.
The alpha i's depend on the solution itself.
The alpha i's depend on the solution. It's true. That's true.
So you cannot move the elements. Because you don't know.
No, I can solve the problem. I solve the problem. I get theta star. I compute those guys. And then I remove them. No cheating.
But it might be more useful to think of it as not removing, but what to keep.
Mm-hmm.
And if you think of it, it's not that why would you remove it? It's more what to keep if you move forward. And this is I think that's the more precise question.
It's a good comment, and I think in the afternoon in Emtiyaz tutorial maybe you will see a very similar looking equation, but for the Bayesian posterior. So and maybe this is a bit what we want to call Bayes-Duality. That here, you know, you can describe your object as a sum of many parts. So that the whole thing is made up of many small things. And if you look at the Bayesian posterior, you will see something similar, that it's also made up out of many little parts. You have your likelihoods. I should write proportional, and maybe the prior. So superficially it looks similar. Maybe in the afternoon you will see that this can be made precise also in the approximate case for operational approximations. You will always have such a representation of the whole thing as sum of parts, and then you can understand which part was actually important for my whole thing, and this can really help you to understand your solution. Oh yes. This is wrong. Okay, so this was another, and then people use this for kernel methods, for example. So if I have my theta star, I can predict using it. Just this is my linear model. I can predict with it. but I know my theta star is the sum of all these alphas times xi, so I can just plug that in. My representation from the previous slide, I know that theta is the sum of all these alphas. And now if I want to predict with my theta, I can just plug it in. Then I can predict with my alphas. Yeah, these inner products, you can generalize these to kernels. Then these x's can also be infinite dimensional. So you have a dual way of predicting where you just need alpha star and x. And then Eugene comes and says, oh, but to know this alpha star, maybe I need to know my theta. So what have I gained? But the big thing is that there's actually a dual optimization problem which can directly search for alpha without the need of ever forming the theta. So you will also, yeah, this is kind of the dual problem. You can see you optimize for alpha in the space of Rn. So for every data point, you have one alpha. And then you can just solve this optimization problem and you get alpha without ever forming theta. And then your theta can even be infinite dimensional. So theta can live in some infinite dimensional RKHS, but you can still solve that dual problem because it's finite dimensional. You just need these inner products. You can use a kernel here, k of xi, xj, and you can solve it. So it can be very convenient for computation. And yeah, this is all well-known things, of course, in kernel methods, but that's also one reason why people like duality machine learning, because you can do things like this.
Can I say?
Yep.
So yeah, if you're working in Gaussian process, you kind of see the duality that somehow the last term doesn't contain any x's now, and they all move to the first term. Right? So if you write the primal, then the last term contains the x, and the regularizer, the first term is simpler in that case. So when sometimes people talk about weight space and parameter space, actually they're talking about quality without realizing it, and maybe do it in a very much more difficult way than you can.
Yeah, and in the dual problem, there's this Fentel conjugate function, A star, and of course, maybe if you have never seen it, it looks very strange, but I will also explain it at the end of this tutorial, like how were we able to find this optimization problem and why is it solving also for these alphas and so on. Okay, and then on Tuesday, there's a third application of duality that's very popular in machine learning. Using duality, you can create convex relaxations. And I will give a very short talk on Tuesday on this. We had a paper last year where we constructed like a convex relaxation of the Bayesian objective using duality. And we were able to connect that to a recent deep learning method, SAM. So these kind of dualities can also be somehow approximate, be used to construct lower bounds, and then be useful to connect different methods with each other. So yeah, so we discussed a bit what is duality. We've seen some examples of how duality is used in machine learning. So this was not exhaustive at all, so there's many more. And yeah, now for the remaining 30 minutes, I will give maybe a brief tutorial on which really explains more in depth what I've just claimed to be true. Is there any comments or questions up to now? Yes. One question here.
Yeah, just a quick question about the kernel example.
Just a quick question about the kernel example.
Mm-hmm.
Would I be right to say that in practice it only works with finite dimensional RTHS? Because the weight space would be infinite dimensional? Like we are kind of forced to always use the dual objection?
No. I mean, the RKHS can be infinite dimensional. You just need to be able to compute this k. So if your k is some exponential kernel, then this is implicitly computing the x transpose x in an infinite dimensional space. But you can still compute this k thing just by computing this exponential function. And then in a dual problem, you never need to form this infinite dimensional object. So you can really solve the infinite dimensional primal problem because it has finite dimensional structure. This finite dimensional structure gets uncovered through the dual problem.
It's finite because the data are finite.
Because the data is finite. If your data is infinite and your parameters infinite, you're lost somehow.
Yeah, that's what kind of means like the other way around, because that's the dual is the thing that we usually solve, but it's like too expensive. And then so I guess the bottom line is I need to have finite dimensional equations.
Okay, you're saying people then go back to the primal, do some Fourier feature approximations in the end, and so on. But yeah, okay, yeah. So, but I mean, you can really solve the infinite dimensional thing.
You can do SVM. They are very sparse. And we start with non-support vectors.
Okay, if there's no more questions, maybe I start with a tutorial. Oh, this has some lag. Okay, so maybe I start with a very innocent idea. If I have a function here, the absolute value function that we've seen, for example, in total variation smoothing problem, I can also write this as a maximum over linear functions. So this p is the slope of my linear function, and then I limit the slope to -1, 1, and I just consider all these linear functions with bounded slope, and if I take the maximum over them, I recover my absolute value function. This is nobody should reject this, right? I mean, this is very straightforward that you can do this, but if you understood this, there's nothing more, that's it. So everything that I showed follows from this innocent idea. So this is basically, if you understood that you can do this, then this is convex duality. You can represent the convex thing as an intersection of linear things. And yeah, you can do this for other functions here. This is the hinge loss for the support vector machine. I just put it for completeness. Then you limit your slopes basically to -1, 0, and yeah, there's some. So you can do this, and you can also do it for quadratic functions. So this I do now because I want to give some example on ridge regression. So we have here our quadratic function a over 2x minus y square. I claim, okay, I can write this over all these linear functions here. So this is really a linear function in x, because it's just p times x. And then I have here my intercept, which looks like this. So you can imagine my quadratic function. I write it really as a maximum over all these linear functions. And then we will see that this very simple way of doing it gives you already things like matrix inversion lemma and 2 ways of solving the ridge regression problem. So of course you can say, is this really true? Or there's really a huge delay actually. Yeah, so is this really true? If you don't believe me, you take the derivative, set it to 0 and plug it back in, and you will see that it's actually true. Let's do this. Yeah, we take the derivative and solve for p, so we know the optimal p is a times x minus y. And then we plug back in a times x minus y for p up here in the maximum. And if you do this, you have this, and then you do the calculation, you see that it's a times x minus y squared minus a over 2x minus y squared, which is a over 2x minus y squared, which is your original function. So I can really write my quadratic function like this. And okay, one more comment before I show how this can be used to derive dual problems for ridge regression. I really want to tell you that if you understood this, you really know everything. So there's the person who founded this field, Terry Rockefeller, or he's like one of the, maybe he didn't found it actually, but he was one of the major figures in the field. He said the basis of duality in the theory of convexity is, from a geometric point of view, the fact that a closed convex set is the intersection of all the closed half spaces which contain it. So he writes this in the introduction of this famous book, Convex Analysis. And I've shown it here on this image. I mean, he talks about convex sets, but convex functions and convex sets, they are essentially the same, because to any convex function, you can associate a convex set, which we call the epigraph of that function. I noted here epi of f. This is basically all the points which are above my function. So I have a convex set, associated with my convex function, and this convex set is simply the intersection of all the half spaces which contain that convex set. And he says all this duality, it just follows from that simple fact. And of course, if I have a non-convex function, if I still try to do this, I run into problems because I cannot push my linear function into the gap. So people call this a duality gap. Because I will not be able to represent non-convex thing through a intersection of half spaces. And you would need other functions. Maybe if you had quadratic functions, you could fill that gap. But for convexity, these linear functions are used. Okay, so let's go back to the very simple example, ridge regression. Actually, there's a 1/2 missing. You have to imagine here a 1/2. And now we've learned how we can write our our quadratic function as a maximum over linear functions. I just plug in that thing. So we've seen this on the previous slide, that we can do this. This is what I just calculated. And maybe now I exchange the summation with the maximum. I introduce for every, so this is actually quite useful trick that I can, because these guys inside the sum, they are not coupled, they don't talk to each other, so I can pull the maximum out and give a pi for every guy in the sum. So I can also write it like this. And if we see min and max, our favorite thing is to swap them. So yeah, we can also do this here. And we already arrived at our dual problem. And yeah, this is a saddle point problem. So we minimize in theta and we maximize in p. And at the saddle point, the gradient both in theta and in p is 0. So if we just look at the optimality conditions for this saddle point problem, well, I have here the function L in theta and in p. I minimize in theta, I maximize in p. And I used a bit more concise notation in the second line here. Sorry, this is a lot of details, but I just wanted to give one example very rigorously. We can see that at a saddle point, if we set both the derivatives in theta and p to 0, we get basically two conditions for our variable in theta and for our variable in p, so this should be theta star. And just using these two equations, we can already arrive at two different ways of solving the ridge regression problem. So just under a small reparametrization, maybe I call my variable p, I rescale it, so -1 over delta times p, I call that alpha. So we see our familiar equation here, theta equals x transpose alpha, and alpha was the rescaling of p. And then just plugging these two equations into each other, we have two ways of solving the ridge regression problem. So I can plug my theta star in here, and then I just have a linear equation in alpha. I can solve that for alpha. I get this way. But I can also solve in theta by plugging the alpha in here, and I get this kind of equation. So I find this quite fascinating. We didn't do much. We just wrote the quadratic as a maximum of linear functions, and we somehow ended up with matrix inversion lemma. So yeah, but this is the essence of duality. You have now two ways of solving the problem. You can compute your dual variables like this. You can your primary variables by solving this system, and you can also predict what we've seen before. This of course connects to kernel methods, to GPs. We can then predict also using our dual variables. So yeah, this is basically convex duality on the very simple example of ridge regression. So until now, was it clear to follow? I hope there was no weird steps that I did. Did something feel uneasy or confusing? Then we can also take a break here.
I have one question. So, I mean, so the matrix learning, so this is how I would have learned this, or I know this, but how do you go from the quadratic problem to the other one? So it looks like it came out of thin air in a way, right? You can show that it's the same thing, but how do you come up with it? So how do you go from the quadratic to the like a analytical way?
I see. So the question was, how did I write the quadratic function as a maximum over linear functions?
Exactly, for exactly just this case. So
yes. So this is a very, so first thing, you can, if your function is convex, you can always, there's a proof that you can always write it as a maximum over linear functions. The only question is, how did I know that this is -1 over 2a p squared? And so it turns out that this guy here is called the Fenchel conjugate of the original function. So you will learn at the end of the talk a recipe, how you can always do this for any convex function. I will give you a recipe how you can always find this representation. The only thing you need to be able to do is you need to be able to compute the Fenchel conjugate of your function. And sometimes computing it analytically is hard. Yeah, so and in the quadratic case, the analytic computation is easy, basically. And, people have figured out analytic forms of Fenchel conjugates for many functions. So. Okay, then, our support vector example, maybe I also talk about the SVM dual, but I actually will skip over it quite quickly. We have here this linear classification example, and if you do train a support vector machine, this is what I showed at the beginning, you have a problem like this, and you can do essentially the same. You can, again, write this maximum as a maximum over linear functions, and it's exactly the same as for the linear regression problem. So I will not go into the details here. Let me just wait for the slides to sync up. You plug in this maximum representation and you swap max and sum, you swap min and max, and you look at the optimality conditions of the Lagrangian, and you can derive your dual problem and so on, and you will arrive at what I've seen, what I've shown you at the beginning. So you can do, whenever you can write it as a maximum over linear functions, you can write the dual problem. So yeah, maybe we go now to Alex's question. So how can we find this representation as a maximum over linear functions? And this leads us to something called the Fenchel conjugate. And yeah, to derive these things, maybe we have a look at our function f, and we have an affine function which is parameterized by the data p, r. So any affine function below my function f, which is like globally below my function f, it satisfies this inequality. So if I have an affine function which is globally below f, it satisfies p, x minus r less equal f of x for all x in Rd. You all agree with this? I just wrote down the condition for an affine function to be below f. Equivalently, if it's globally, for all x it's below f, I can actually rearrange my equation. I put f of x on the left, I put r on the right. So if my data p, r is such that this affine function is below f globally, then also the supremum of p, x minus f of x is less equals r. This is just writing this for all as a supreme. If it holds for all x, it holds also in the worst case, which is the kind of the maximum. And then if my linear function, if it touches the graph, it must hold with equality, right? Because at some point, I mean, if this guy, if it touches this one, then for some x there must be equality. So if that guy holds with equality, supremum p, x minus f of x equals r. So they have connected. Then we have this equation, and this quantity here, that guy here, that's already what people call the Fenchel conjugate or the Lejeune-Fenchel transform of my function f. So it tells me this function for a given slope p tells me how much can I push up my hyperplane until we hit the function. Sorry? No, x is here, it searches over all x. So this is like a global lower bound for all x. And it can touch at one point, or it can also, if it's like linear, then there can also be multiple points. Okay, so I have 10 more minutes. Then maybe I can answer his question. So how can we use that now to always write our function as a maximum over linear functions? So there's this nice theorem which says if my function is convex and continuous, or it's enough to be lower semi-continuous, then the following always holds. The function itself is the same as applying this transform twice. And then just a definition, we can write our f of x as a supremum over p, xp minus f star of p. So if you're able to compute f star of p, you will always be able to write your function as a maximum over linear function. And this only holds in the convex case. So for non-convex functions, there will be a lower bound actually. Because you can imagine I cannot push my linear function up into these stands. So what I will end up actually for this convex representation, which is called f double star, it will be the convex envelope of my function. So this gives you some kind of systematic way to construct these dual representations. So yeah, maybe I have a bit of more material, but I think this was the most important part. If there's questions or comments, then otherwise I can show maybe some results, also some more results.
Yeah, so just to like make clear what you said before, so like now if I have any function and I want to find this solution autograph into like transform thing, like in principle I just look it up in some table for known functions and I construct it based out of different parts, or like there's some kind of rules for this?
Yeah, you can look it up, or you can try to compute it yourself. So you can just say f star of p, so supremum over x, xp minus f of x. And then you just try to solve that optimization problem. And then you have it. And often this can be, I can solve for x in closed form, you plug back in x and you have it. So if it's like one-dimensional or something, you often can do it. And also in higher dimensions, if the function is simple enough, you just need to be able to compute this guy. Okay, so there's a very general way. I've shown these two examples just by plugging it in, and you can of course do it in the general case where you have two functions, f and g, two convex functions, and a linear operator a. And okay, maybe I skip over this very quickly, but what I've done kind of manually for linear regression, you can do of course abstractly for any convex function, and you do lots of calculations, and you end up with two dual problems, one here and one down here. And then you just need to be able to compute these conjugate functions, and you don't need to go through these steps anymore. You just compute these conjugate functions and you have your dual problem. It's interesting, like you said, transpose is the dual, and we see the dual problem, you have the transpose, so this was quite nice. And yeah, so this includes all the previous examples as special cases. We've seen the ridge regression, we have seen the SVMs, we've seen the total variation smoothing. These are all special cases for specific choices of f and g. So this is a very powerful general framework. And yeah, these dual variables, maybe I skipped this, but they can also be seen as Lagrange multipliers for a linear constraint. So these alphas, if you do the calculation, these are just Lagrange multipliers for a constraint. But maybe more the interesting part is, why are these dual variable sensitivities to perturbations? So this is one of the last slides I have. Let's consider our general problem in theta, f of theta plus g of a theta, and we perturb our edge. So a theta was the value at the edge, and we perturb our edge slightly with some variable xi. Then we can look at, given a perturbation, we can look at the minimum of our problem. So how does the minimum value, so p of 0 is just the minimum of my original problem. But I can look at p of xi, which is a perturbed version of my problem. Then there's a theorem which says that the dual variables measure the sensitivity of this perturbation function at 0. So you can prove under some regularity conditions, and if this function is differentiable, otherwise there exist generalizations, that the dual variable alpha is the gradient of this function p, which measures the minimum of my problem at 0. And yeah, I have some, maybe I share the slides later on Slack, but there's a really nice book, recent book, where this is very beautifully explained and motivated. So yeah, that's one explanation why these dual images look like they look. It's basically the gradient of under perturbations. You can imagine if I perturb my edges here in that image, my minimum would change a lot, and then you understand maybe now why the dual variables look like they look. Just as a general comment, this I showed everything in Rn and Rd, but this is actually very general. So if you check this original paper from 1967, this is already done for general vector spaces. So we have here E and E star. These are two vector spaces in duality. So they can be infinite dimensional. They don't have to be Rn. The dimension can be infinite, so it can be function space. There's only some technical conditions that they have locally convex Hausdorff topologies, which I maybe don't know exactly what it is, but it holds in a very, very general setting, this duality. One example that is used a lot in machine learning is that your primal space E is the set of measures on some bounded set, and the dual space, or the other way around. I mean, I think it doesn't matter here because it's paired space. The dual space is the space of continuous functions. And I think you see this a lot in machine learning. Applications also of this duality theory in infinite dimensions. There's, for example, in Bayes, people use this Donsker-Varadhan lemma, but this can be seen as a way of writing the function as its biconjugate and so on. So the only thing I want to say here is I've shown things in Rn, but they hold in a much more general setting, and this can maybe be useful. So yeah, that's it. I think perfect in time for lunch. Maybe as a quick summary, what did we learn today? We discussed a bit what is duality in general. Maybe we should have a bit of a more open mind. What we call duality. We've seen some examples of duality in machine learning, and I've showed you one specific duality which we obtain by representing a function as a maximum over linear functions. And we've seen that this gives us interesting things in machine learning. So yeah, thank you very much.
Maybe one question.
For the Fenkel-Rockefeller duality, the minus sign inside the G is a bit odd. If you go back a few slides.
Yeah, I think it's quite slow, but maybe it's, yeah, okay, I'll try it. It's odd, but it turns, if you do the calculation, it turns out to be like this. So it's minus, so because the dual problem is a maximization, you want to maximize two concave functions. You mean this minus here?
Yeah, so particularly if A was I, you seem to have asymmetry you would expect.
Yeah, but this is just how the math turns out to be. If you check Rockefeller's paper, it's also in there. So this minus comes, I think, you write the minimum as a minus maximum, and then you get the minus. This is some more.
just how the math turns out to be.
It's another duality between the maximum and the minimum.
Sure.
If you want to replace the minimum, then you need to.
I think the thing I can't wrap my head around is if A was I,
Uh-huh.
then F and G are not behaving the same way.
Yeah, but this is the fancy conjugate function of F. So this is not F, this is F star.
Right.
Yeah, so this is completely different. Well, not completely different, but this is like a different function. So this was the minus is still there if A is I. So. If you don't put the minus here, then it's wrong, so it will not work out. You will, yeah.
I guess what you're saying is if F and G would swap places here, it would be the same, right?
Yeah.
So would this also be true, like if you put the minus in front of the G star minus instead of the F star?
Yeah, you can always say my A tilde is minus A. Like you introduce A tilde, which is minus A, then you can put the minus. Yeah, you can, instead of minimizing x, you can always minimize over minus x, and then it will be the other function.
The other way to say is that, for Bayesian, sorry, not a question, but for Bayesians, I think you can think of F theta as the prior regularizer, and then F star theta is the G2 prior. So A is the somehow cardinal related. So A there is like feature matrix, then A transpose there becomes cardinal matrix. It's in the data space, it's the transpose. So if it's n times D, then A times theta is worth acting on D, like the dimensions. A transpose alpha is acting on the data side, on the other side. So that's the easiest way to see it. But we never write our change variable of integrals in this way. But when we go from linear model to GP, we use the exactly same relationship, but with integrals. Then it's not confusing.
Yeah, let's thank Thomas once again.
I think everyone know Emtiyaz Khan, aka MT. So he's a world-class researcher.
Are you making fun of me or introducing me?
Developing using a Bayesian method to highlight how can we learn from data. And so he's a team leader here at RIKEN, leading the approximate Bayesian inference team. And previously he was in EPFL with his postdoc there. I think he's a great pedagogue and teacher because he won some awards there for teaching. And previously he was doing his PhD at the UBC, the University of British Columbia in Vancouver. So have been all over the world, and he will explain us the Bayesian learning rules. So thank you.
We didn't plan it this way, but I think it came out as a revenge that a conformal prediction guy is introducing the Bayesian learning rule. But it wasn't planned, but I guess the universe works in the way that Bayes wanted. Okay, so I could have actually done my usual Bayesian learning rule thing that I do, and it's a talk, and it goes over the paper in a, in the way that it's written, and I think it's not interesting for this kind of audience, because this is a small meeting, and some people are in Zoom, but I wanted to try a different way to do this, and I don't know how it will go. This first time, it's possible that the math is a little bit too much. I think math is very simple, so I'm just going to talk about sample mean, more or less, but maybe there's too many things here and there. I hope it makes sense, but I don't want to give too much because you can actually read the paper, but I just want to give away how we actually think about Bayes rule, and then why Bayesian learning rule is a natural extension of that. So just kind of give that perspective. Okay, And the perspective actually is really this, and I'm so happy that Howard already had a really big slide on optimal information processing. I don't know if you were at his talk, but he showed this paper by Zellner in 1988. And the title of the paper is Optimal Information Processing as Bayes' rule or something like that. But this is how we think. So I've been thinking like this because I actually learned Kalman filters and this kind of methods. That's how I grew up. So I always thought of like online learning and information processing in a sequential way. And then whenever you start to write that thing down, it comes out to be like a Bayes' rule. So this has become kind of a belief for me, where I see that the scientific principle that I'm vouching for is that whenever you have information processing, then there is some kind of Bayes' rule there. And you may not first recognize it, but it somehow enters in some way, and it's fundamental. But it's not just because, oh, we are Bayesians, we like our Bayesian models and stuff like that. But this, you don't need Bayesian model for this. But whenever information is somehow added in the system, then Bayes' rule just is there. And that's what I want to say. So all of the work that we do is actually really supporting this. So we choose to work on lifelong learning because it's an exciting problem for understanding information processing, because things come, slowly over time. But you can actually call it many, many things. You can call it online learning, continual learning, incremental learning, or just learning for a very long time. There's a sense of time. But you can also think of it as distributed learning, so like federated learning and other kind of concepts, decentralized, distributed. In a sense, what I'm trying to say is that somehow knowledge or information, sorry, I use the term interchangeably, is spread across time or space. And our space, right? This is the simplest description that I could give to this problem, that is about information processing, because it's coming from different places and you have to somehow put it together and make sense of it. We do this every day as humans. So we want the science of this, and I think the science of this really points towards Bayes' rule, not Bayesian models. Bayesian models are great as well, but Bayes' rule is more kind of easier to apply more universally, because it says less about like what you're applying Bayes' rule on. So let's think about like, in this context, think about a brain. I don't know how to draw it, but it's something with something at the bottom. I don't know. Okay, that's a brain for me. it's something like this. Okay, and then the brain lives in the world, so it somehow sees some data over time. And I'm thinking more like incremental or online continual, but it could also be over space, right? It's many things pointing from different places. But when you start to write it like this, I think it is interesting, because then you can start to think about how information is processed or added together. So in deep learning, like usually people would say, I'm gonna update my parameters. Well, people don't do this, right? People usually, they have, let's say, like a batch. So maybe you have all of this D1 to D4 at the same time, and your goal is to learn theta 4, right? That's how people see it. But it doesn't mean that if you're not seeing things sequentially, it doesn't mean that this structure is not there. It's somehow there, and it should show up. So I'll try to start with the online setting and then try to comment on the batch setting, of how the online setting helps us to understand the batch setting, why our algorithms look certain ways, why they look like stochastic gradients, and sometimes they look like atom or some Hessian being there, and that should be better somehow, but Bayes' rule will actually tell you that it is better for a reason. Okay, so maybe to make this a little bit more concrete, these kind of algorithms, so let's call them deep learning, so deep learning perhaps, they will have an update like theta is updated using some kind of gradient, right? And the nice thing here in this in this setup is that you are adding something. Ultimately, what you are doing in the sequential version is that you're adding knowledge over time, right? But even in the batch setting, you're somehow using gradients to add things to your parameter. So somehow there's an addition going on. So the knowledge is added and improved, and the model is rich over time. It's somehow represented in theta. We don't quite understand how that works because we are always doing batch setting. But if online setting, it's easier to understand, is a point that I would like to make. In Bayes' rule, this is same thing is realized slightly differently. So you have posterior, but then you you multiply. So maybe this, then you could say it's an old posterior, and then this becomes the new posterior. So you have a new likelihood, right? So you multiply, and here it's a multiplication. It's not addition, but as you can kind of think that if I take log of everything, right, then it will be some kind of addition, right? This is the old one, this is the new one, okay? So you can sort of see that in log space of the posterior, somehow there's addition going on, and there's also addition going on in the gradient update, and there should be some similarity between these. So Bayesian learning rule is all sort of like putting these things together in the framework that information is added somehow, okay? So in general, what you actually will see, maybe I'll give you the thing that in the end what we will learn is that somehow this addition, so I will introduce something like lambda new, and then I'll represent this by lambda old, and this will be a natural parameter space. Okay, and then you will see that this is somehow the new information that's added to it. It's actually natural gradients. So they've kind of, the idea is that it's also gradient, you know, in the Bayesian side, but it's a special kind of gradient that's using some kind of duality. So it's computed in a dual space. So addition happens in one space, in the natural parameter space, but this computation happens in the dual space of the natural parameter space, which we call moment space, expectation parameter space. So I will maybe denote it by mu for that reason, because it's expectation. Okay, so you will see that if you make right choices, then you will recover this. Right? So there's kind of a mapping between these things. The addition in this space is also addition in the gradient space. Okay. Any questions on big picture side? It all makes sense. Am I going too slow? Is this too slow? No. Good.
I have a quick question.
Yes.
Yeah, I like the point about the addition, but I was wondering, like, maybe in the continued learning case, we might like addition doesn't increase the dimension of the parameters. Does that say something about Bayes' rule, or does that make sense?
No, addition is not increasing the dimension.
Yeah, which is maybe something that we kind of would expect.
Should we?
Yeah, that's the
okay.
question.
Well, if your parameter space is like same, then it shouldn't, right? It's somehow you're increasing the data, so its effective dimensionality is increased as you increase the information. So sometimes you know more. And what is that is a question, and I'm kind of suggesting that question, there's a relationship between parameter space, like on the left hand side and the right hand side, and there has to be some bottleneck in between. which will be effective dimensionality. So the dimension of the parameter space and how much knowledge you add as data incrementally, they interact with each other. Yeah. Does that make sense? Yeah. Okay. So what I will try to do is I will try to like define, or not, shouldn't be define issue. Let's think about it. So think about what is new information, what is old information, how to, characterize them, and then we'll see that once we understand what is new and old, then there's a way to simply add them. Okay, and that the addition happens. I call this conjugate computation, but you don't have to call it. But it's addition in a space which is where somehow things are kind of added easily. I'll make that clear in the next slide. And then Bayesian learning rule is basically generalizing that. And so I think we will run out of time, I'm very sure here. But I thought, maybe, who knows, right? Maybe we can actually get till here, but probably we'll never get to the dual part of it, because still explaining the previous part to the community that was done like 7-8 years ago. So I apologize. Maybe the next meeting it'll be clear. But I put some of the papers here that I will base this on. Okay. So actually this bit that I did here, I would recommend you to go in the BLR paper. And so BLR paper starting is like this, right? I don't know if you've seen it, but it's a beautiful paper. So I love the authors. Okay, so sorry. So but you can actually if you want to start read it properly, then you should go to the end. Okay, so this is what is written here, and this is like maybe our Bohemian Rhapsody. It was written in one discussion in one go. Howard and I just talked about this, and then it just came out, and then we changed a few words, and it was just perfect. So these things are kind of written here, that good algorithms somehow should be Bayesian, and it comes from these ideas of Zellner. So please read this, and it'll make more sense after I have given this all this talk about information addition, information processing. Okay. So yeah, my hope is that I can point to the paper, and then maybe later on you can actually read the real thing. Everything's going to be like very cartoonish in this talk, because I'm trying to just make a point, and as long as that point is being made, we don't really have to go too much into the detail. Okay, so let's think about addition, right? So when we say adding things, right? Adding knowledge, adding information, adding data, adding something. You can also think about subtraction, but addition is enough. Subtraction is just the opposite, right? So the one view to look at information processing is addition, right? So the simplest form of addition that you know is one-dimensional, right? Vector addition. So like you have a number, right? And then you have a much larger number. Sorry, it's not as large. Let me make this smaller. So small number and then large number, right? And you know that when you add the large number to the small number, it becomes big. So you know that you have gained something. Right? This is quite nice. I mean, it's very easy in one dimension. But if you go to 2 dimension, things looks a little bit more tricky. But maybe not to you. So can somebody tell me how do you add things in 2-dimensional? Okay, that's one way to think about it. You add twice, right? That's one way to think about it, which is correct. And this is how they teach you in high school. And in a sense, the education has failed you. I'm sorry. But you're correct. You're not wrong. But there's a better way to think about it. In the sense that if you have to add something to something, you first have to think about what is common between them and what is new. Right? So this view is more like if I have a vector and then I get another vector. Right, so this is old, and this is new.
then what you can do is that I on purpose I chose it to be horizontal, but it doesn't have to be. You can always project this onto this, right? And so you're right? You're doing two additions in two orthogonal directions, but you can actually also see it as first figuring out what is common, right? And so this is in the direction of the old thing, and this is the new thing, right? So addition necessarily has projection in it, right? So you project. So maybe let's call this y1 and this is y2, and you'll somehow take y2 and you'll try to project it into the direction of y1, and then that projection will somehow define these two things that you get, right? So what I'm actually claiming right now is that when you are doing Bayes rules, so let me also complete this by saying y1 and y2 is easier to do this here. But if you're doing Bayes rules, so if you had, so let's say if you've observed something, so theta is the parameter, you've observed something, so you had a posterior, and then you got a new observation, then somehow this one is absorbing both of them. It's the posterior, right? So this is clear that this is old posterior, this is new posterior, and this is the likelihood that's time 2, right? Now you cannot directly see why it's actually doing this kind of projection. It's not very clear right now, right? So that's why I think when we write Bayes rule, you cannot quite see that, oh, why is it connected to this kind of vector addition? But there is a huge literature on this actually. I don't know if anybody knows about this guy. People who know Kalman filter should know about this. No? Okay. So there's in linear estimation, I don't remember but this is how I learned this. And actually my first ever note in my life that I wrote, which is on my webpage. If you go to my publication page, scroll down. I don't have that many publications, so it'll be fast. And just scroll down and go to the last one, right? You will find a note that I've written about this particular thing. So actually what you can show is that you can embed these probabilities. You can see them as random variables as vectors, and you can go into the vector space. So you can kind of then do this procedure through, I don't know if people know linear algebra, remember it, but there's a process called Gram-Schmidt orthogonalization. So essentially this projection goes down to doing something like SVD style thing, like you project new vector to old one. So that's a kind of more maybe mature way of seeing addition, right? You find the basis and you project the new thing to the basis, and then you update the old things, but then the new thing, you add another dimension to it. Did that make sense? Everybody knows linear algebra, am I boring you? Okay, so you can do the same thing with Bayes rule, and this is how you can derive like least squares and Kalman filters. So this is what I learned, but all of this works only for Gaussian, so it's not, not Gaussian, but like something with two moments, and then you can do these calculations. It's quite beautiful actually. His name is Thomas Kellott. The book is published in, I don't remember actually. 2000, okay. Yeah. Okay. Now what I'll try to show you is that Bayes rule actually doing something very similar, and gradient descent is also doing something very similar. Okay. So do people see it already? Does gradient descent do this? Who sees it? When you write gradient descent, does it do some kind of projection like this, where it's trying to find common things in the past and new things in the future? Okay, we're not going to be finishing this tutorial in time. Okay, so great. So then we have lots to talk about, and it's not even Bayesian. It's quite easy. So let's start with the simplest one, right? Sample mean. Okay. Yeah, I already wrote the wrong one, but let's say I have, so let me actually also write it. So I'm doing this notation, so I'm writing n. N is not iteration of the algorithm, so very, very important. N is the sample size, okay? And I am defining theta n to be this. It's a sample mean, we all know it. And then we can observe one more thing, right? yn plus 1, and then you get a new sample mean, right? So my question to you: what is new information and what is old information in this? Can we have some suggestions on that? There's no wrong answer actually. They're all correct. They're just incomplete, perhaps, or different. So what is old information in this setting? How one could define it? Simple answers are, you're correct, huh?
Y1 to n.
So old information is y1 to n. All of this is old. And then yn plus 1 is new. Okay, that's one way. Are there any other suggestions? Yes. So you could actually do just theta n. What did you say? Can you repeat it?
N times theta n.
Wow. N times theta n. I like this. You already in natural parameter space, actually, it turns out. So then we can go fast if you know this. Because when I ask people, they say theta n. Y1 to yn makes sense. Y1 to yn is a little bit cheating. Because it makes sense. And it's actually correct completely. But it's the dual view, unfortunately. But the more primal view is that you give me theta n. But theta n is actually partial answer, right? So you actually also need to know how many samples you've, because otherwise you don't know the next one, how much it was. Was it 10,001 or was it 101 or was it like 11, you know? If you've seen 10 or 1,000 or 100, you don't know. So you need both, right? And does that make sense? So you can actually really formalize this quite clearly. You could write this thing down. So you could do a little bit of manipulation. You say, oh, there are many ways to do this, but let me just do one. Oh, I like subtraction actually. So because I want to subtract old information from things, so I do this, okay? And then I can also add it here, right? That has changed nothing, right? And then I could rearrange it, and I can get, oh, wait a minute, did I do it right? Oh, I shouldn't have tried a new one. Should have just gone with my notes. I should be able to do it like this. N plus 1, yeah, makes sense. N plus 1, yes. So this is then theta n plus 1 divided by n plus 1 y n plus 1 minus theta n. Does that make sense? So it's just, did it make sense? Yeah. Oh no, it didn't make sense. Eh? Oh, it's that's the answer that I know, so god damn it. Okay. I'm gonna do what my notes say here. Then so I will remove this as boring. This is n, then I'll do y, sorry, I'll write this as yi, then I will add yn plus 1 here. That makes sense, right? So I just took that out, and then I know that this guy is, as somebody said, it's n theta n. So then I get an answer which is, did it die? Sorry, not working. Oh. N divided by n plus 1 theta n plus 1 divided by n plus 1 yn plus 1. This is good, right? One way is this, but then the even more space. But then the other way to write this would be, what the hell's going on? Would be to to write it as theta n plus 1 divided by n plus 1 yn plus 1 minus theta n. Basically what I did is I added plus 1 and subtracted my 1. And then n plus 1 divided by n plus 1 gives me this. And then 1 of the minus n goes in here. Okay? So there are two forms I wrote here, and they both seem kind of okay, you know. In one form, you would think of, so this one is old, and then this one is new. But you could also say that I would do weighted sum, so you could maybe call this one as old and this one as new. But it doesn't seem that satisfying, so I'm not going to do that, and maybe later on it'll make more sense. But does this make sense? Does it remind you of any algorithm that you know? Gradient descent, oh wow. So you see that actually we don't write it like this, but this is not iteration, right? N is the solution of a, let's say solution of a batch problem with n plus 1 examples. You can write it as a solution of the problem with n examples. And so you're kind of doing this rewriting things in terms of old things, and then you can see the new thing, right? I hope this makes sense. I'm rewriting theta n plus 1 in terms of somehow theta n and ny plus 1. But you can also see that I need an information about n, right? So, well, if you don't see it, let me just say a little bit more concretely what I mean. So you could actually start this in the gradient descent way, right? And there you have to start with like, oh, I'm going to write a loss function. So I'm going to define ln of theta. I will omit theta for simplicity, but I'll just write it to be something like square loss, right? And then if I do the gradient of, if I do gradient of this guy, then I will get that, right? So then the gradient, well, gradient descent algorithm would not be this, but you can write this update in terms of the gradient, right? So this is the gradient at n plus 1, and I omit that it's evaluated at theta n. Now let me write it. Okay, and then you have to add a step size somehow, right? So you have to make a decision. Like it's the same thing that you have gradient and you have step size, so you need another information. Yes?
The sign negative.
Ah, sorry, yeah. Thank you. Right? I mean, it's addition with a subtraction, but yeah. That makes sense to you, right? So gradients are defining new information here, but they're not complete. You need step size also. Is in the same way that the past, the old information is not sufficient to just say theta n, you also need n. So if you actually knew that rho is 1 divided by n, you'd converge in one step. It's just you use the old thing and then you add the new thing. I know batch people were never happy. You'll squint at this, but this is not batch. Right? I'm just trying to write the algorithm as a gradient. Yes, gradient as new information, let me just say, yeah.
What is the, can we see the projection that we have talked about last slide on these two examples?
I don't know actually, but like, this is what I'm trying to say. Maybe you can interpret this as a projection. But, so you can interpret this whole thing as a projection. So like this, sorry, I should maybe have said this whole thing. So sorry, did I, like 1 divided by n plus 1, yn plus 1 minus theta is some kind of projection on the whole thing. I'm not claiming that it is. I'm actually not going how to define projections in usual sense, because there are many ways to do it. And this is the problem, like if you start to talk about gradient descent, Newton's method, projection is always different. Okay, but in base rule, it's only one equation that will always give you this answer. Like whatever answer you want, it will always return you the optimal one. So that's kind of the next point that I want to make. I think I've made many people uncomfortable. Nobody seemed to be happy. No? People have. Hussein is not happy.
The way you define projection is.
Yeah, I haven't defined it.
Yeah.
I didn't define
Using it.
I'm using it, abusing it maybe, yes. You're right. I am doing that.
You apply twice, you get the same as if you applied once. Mathematics.
Really?
Yes.
So this projection is actually correct in that sense. So this, if you go and read Kalat, this is correct. This is exactly, it's called projection. You can go and read.
Yeah, it's only in the Gaussian case.
Yeah. Well, not Gaussian, like the second moment.
Yeah.
So random variable, like, sorry, I'm gonna get to you. Norm is defined as the expectation, and then the inner products are defined as a correlation, like expectation of x times y, and that's the projection. So you can actually read the note that I wrote in 2005. It's just an equation.
You can do all these time series in this kind of projection.
Yes. So Kalman filter, you can derive it in exactly this way without assuming that it's Gaussian. Actually, that's why they were doing it at that time. Does that satisfy you?
I need to see where you're going with this, because then maybe I can come back and see, okay, this is how I should connect the pieces.
Yeah, I'm just saying that you usually see projections in usual algorithms. There are different projections, but in Bayes, it's only one equation always. And there's no notion of projection there. It's just addition. So, okay, maybe I didn't say it, but let me say it. Bayes is more like this. Okay? And this is I don't know, should I insult optimization people? So this is like the world of optimization. So when you actually work with mean, so I think Howard also said this, mean and covariance, this is the, let me use the word shit you get into. And you have pages and pages of derivation of Kalman filters that nobody understands. But if you are in the top case, it's just addition. So of course I understand that in the end to derive the update it takes time, but if you know that we are actually just doing addition, and then conceptually we understand that we are adding information. And then there's a value of information, how big or how small it is. So the quantities that you add, you can just look at their magnitude, and then you can decide how big they are. So they go back to what Thomas was talking in his duality tutorial, that it's sum over things. That's where we're going. In the end, we'll see that this picture will essentially be sum over all the natural parameter or natural gradients actually. So left-hand side is the natural parameter, and the right-hand side is sum over all the past natural gradient over every. So information at every step is natural gradient, is what my claim is. It's a bold claim. You shouldn't accept it, but you should read the paper. It's interesting in that sense. You will be convinced as you look more at it. Certainly I am. Does that make you happy? No. Less unhappy? Oh. Oh boy, I got a tough crowd. Yeah. Oh, sorry.
So if you look at y1, yn as class information, and you look at it as a vector in Rn, you project it onto the line 1 on 1. So if you project y1, yn as a vector of Rn to the first diagonal, the coefficient of the projection will be the mean. Will be exactly the mean. And the second part will be the residual. Yes.
Are we talking about projection?
Yeah, orthogonal projection.
These are projections. It's not a made up. I'm not a mathematician, but I'm not abusing notations. I'm not saying BS. It's just that I'm in a world where I combine ideas from many different places. So to half the people, it doesn't make sense. Well, to 90% of people, it doesn't make sense. Every concept that I talk about, but that's the fun of it. So someday you'll be happy. Online learning. Okay. All right. So the Bayesian world is very complicated now. So you can also do the same calculation with the Bayesian thing. You can write likelihood, and then you can write them as probabilities. So, right. So likelihood is like this, and then you can maybe you can see them as like, so we will use Gaussian in this case. And again, there's no reason why we choose this, but it's basically like choosing loss. So it's same kind of calculation. It's e to the power of minus L, fine. And then I am going to call my posterior as this. So it's like something that I have learned till now. And there comes the choice, and I don't know, but in this case I'll make a choice of something Gaussian again, like this. Okay, so it's also the same thing, but it's a probability over theta, so that's why I switched the order of theta and theta n. But here again, like I have to make a choice, and it doesn't become easier. I'm gonna call the precision parameter to be Sn. And you can see that, you know, rho and Sn, they are kind of similar things that you have to make a decision about how confident you are in your, like how much you know. And can anybody guess what Sn should be in this case? Yeah. Okay, somebody said, but any answers? It's n. It's the sample size, and essentially it's very similar to choosing rho, right? Rho is n+1 step size, and in this case it's that. So now if you did this thing, like, you know, posterior n+1 is equal to this, and then I'm gonna say it's gonna be something very similar to the prior, but I'll just denote this by theta n+1, and I'll have an Sn+1. Then these are two parameters, and actually there's a very nice formula for this which coincides with what is written up. So theta n+1 is equal to, does somebody know this? Actually, a simpler way to write it is Sn+1 is equal to Sn theta n plus Yn, and similarly you can write Sn+1 is equal to Sn+1. Okay. It looks like I'm doing something weird, but actually I'm doing like a two-dimensional addition now, right? And from this calculation you can, so here, okay, so here, should I do the mistake? Maybe I'll just do it. Okay, so this is kind of like, I'll call this lambda n+1 for some reason, and I'll call this lambda n, and I'll call this lambda tilde n, and we don't know why I'm calling this, but these lambdas are actually 2D things, huh? Okay, so, but you can just simply add things in this manner. And if you just add it like this, and then you do the calculation, like you scratch this and you put this here, but Sn+1 is Sn+1, then you get this, right? That makes sense? Everybody's happy with that? I did it a little bit quickly, but everybody's happy with that? No? Okay, sorry.
I don't get where you get that first line. Sn+1.
Oh yeah, I didn't explain it. It's just the property of the Gaussian. I'll derive this in the next slide. But for Gaussian, you could show that the means, and yeah, I'll derive it. Sorry, but yeah, but it turns out that if you multiply Gaussians, you kind of get the same results. But in this case, you're doing two additions, not one. But the result of those two additions is essentially equal to like what's written here, maybe this version. Okay, because so let me just finish writing this one, and then we can make those comparisons. So I'm basically saying this is Sn+1, this is 1 divided by Sn+1, and you can see that if you set Sn equal n, then you will recover that. Yes. right? But my point is that this formula appeared as a weighted sum because I did a simple sum in a 2D space. And this thing repeats forever. That's all you need to know, actually. So when we want to add information, they may not seem like adding like this kind of addition, like what is shown here, this addition. Hope you can see. Yeah, it doesn't seem like that, but lambda 1 plus whatever I wrote here, lambda n plus lambda tilde n, you can simply add them, but the consequence of that is that you get this kind of weighing thing here, which has right. So this one is like is like projection kind of thing, and there's some weight in front. And this one, there's no such thing. Let me actually remove this thing and let's stare at it. I hope that you're satisfied that these two things are equal. Then I can just go back to my form that I love. But in this world, it's just addition, right? And in this world, it's kind of subtracting the old information, reweighing it, and then adding it, right? But this is equivalent to this in some sense. And this one is somehow lifting the space from 1D to 2D. So then here there's a plus. So here you can just see that this is old information, this is new information. And now what I'll show you is that this is the natural parameter space. And there's always an addition. It's not just for Gaussian, any exponential family. And when these things are not in that exponential family, then you can project them. So then these will be natural gradients. That's kind of the point of Bayesian learning. So the new information is always natural gradient. It's going to be some kind of gradient, not this gradient, natural gradient. And then these guys are natural parameters. And then you can rearrange them to write them for somehow the mean of the Gaussian. So you can derive RMS prop like this, Newton's method like this, and it's all the same calculation. And you can see what is the new information in that RMS prop. When it's written in weird way, like this kind of way, it's unclear. To me, it's weird. Maybe that. But that's why I ask you, like, what is new information to you? And that's one way projection is one way to describe it. Unfortunately, we're not familiar with that, and we find that questionable. But you should look it up. It's very beautiful theory in signal processing developed in the 90s. Really, really beautiful. Seeing random variables as vectors. In vector spaces, you can do everything. But that only works for linear estimation. So how do you do it more general is through natural parameters and natural gradients. And there's a duality, and you will not get this property in any other space. And this is kind of the crux of my work. And people are not citing me for this reason because this is not useful for anybody right now. But so it's not just any information geometric optimization. It has to be natural parameter. Yeah, it has to be you. It's like that. I'm in love with this concept. So we call it lambda space, lambda magic, all sorts of words. But you cannot do it in any other space. And that's why this is special. And I'm still waiting for a counterexample where it's not the case. So if you have one, that would be fun to talk. Okay. Oh, sorry. Yeah.
So I was just wondering, you said essentially this whole adding thing, we can see base rule in log space, right, where you just add log prior to log likelihood. But I guess there it's annoying because you always have this log marginal likelihood that keeps changing and pushing things around, right? So are you saying that essentially the natural parameter space is the unique space where your log marginal likelihood will not change in that way? Is that one way to see it?
Am I saying that? No. Actually, maybe it's simpler than that. What I'm saying is that you don't have to write Bayes' rule in probability space because you always know normalizing constants. For exponential families, you always know normalizing constant. So you don't have to integrate things because you know that as long as lambda is valid, natural parameter is valid, it is a distribution. So if the Sn doesn't go negative, then it's a Gaussian. So if you're always adding things, it's fine, right? So then that's why you don't have to do integrals ever, because integrals are done in a lookup table somewhere. Read the VB Made Easy paper, which was at AABI. I don't know who runs that conference, but you do, okay. But this was kind of again explained in that short note that I wrote. So, right? So it's VB made easy because you don't have to ever do integrals. You just do addition, and so that's why non-Bayesian people are doing okay, because they're just doing something that makes sense. It's correct.
Just to comment on the question about projection and all that. I read your 2004 notes just now. And, and the setup that you have there is that you have two different observers both making observations. So there's a y and a yj, and the correlators that provide redundant information, and that's the projection that you have to do. Now, here in this example, the yi's are all conditionally independent, and so there is no projection to do. They all provide separate information. That's why projection is not showing up.
Like in the sample mean case, or
in the sample mean case, the one that you have.
Yeah, so yeah, it's kind of weird to. I agree. Yeah. The model is like every time you observe something, and then you have epsilon, and epsilon is always different, right? So I agree. Yeah, it's all IID. So that's why if you look into theta minus y, then they're all IIDs, and then they can simply be added. That's the principle. So that's why I call this. Actually, there's an alternate derivation that I did for Zedong, who did all this and was like, what is this? But there's another derivation that you could do for this. Like you could basically say that all of these guys are independent of each other and their means are 0. So you can simply set 0 on this side and then you can add all the increments up. So gradients actually, it's a gradient equal to 0. That's the optimality condition. That comes out to be expectation of the errors being 0. First order condition comes about at expectation. This will never ever fail you. This is the principle. First order stationarity conditions are related to expectations, and second order stationarity conditions are related to covariances. Precision, actually, to be fair. And natural gradients somehow combine it in a space where things are just added. So they are weird, and that's why I think it will take years to appreciate this, but yeah, they're weird for this reason, like it's already in this example. Here I'm multiplying by the weight, so I'm actually looking into the space of the precision times the mean. And there, what I'm saying, things are additive in that space. And this is not just me. I mean, if you go Bayesian brain hypothesis, this is the work that they did in 2005, where they show this on experiments with real people, that if people, when they make decisions about two things that are different, they add their uncertainties in exactly this way. So if you ask people to do experiments where there's like texture versus color, I don't know if that was the experiment, but let's say that there are two orthogonal things, then people make decisions about two different things in exactly this additive way. So you can actually ask them to do two separate experiments, and then you can combine those two and predict the outcome of how they will combine it. They will do it like this. It was quite big actually in the neuroscience community, I think, but maybe it has died down. But it's that same calculation which we see in gradient descent all the time, right? And then there's all this question, gradient descent, does brain does gradient descent? I mean, come on, It's more like information processing is happening, and information is represented in a certain way, and it has to be edited somehow in some space, otherwise it won't make sense. Things will improve, or subtractions, you forget, right? These things have to happen. Okay, 5 more minutes so I could actually do this calculation and then take a break. Sorry, Jessica, I just threw this without actually explaining anything, but let me try to do this calculation for people who didn't follow how this equation came out to be. right? Let's just write it down a little bit and hopefully. So point is that whenever you multiply exponential families, so Gaussians are exponential family, then it's automatically adding new information together. That's the kind of point. So let's start with Gaussian. Just do this very quickly. So I wrote this, see, calculations are always the same. Like I had Pn, right? It was proportional to exponential of a quadratic. So I'll do log, and log it will be, so I'll write proportional, like it's there's some constants, but let's just ignore them. Then it's something like this, right? Does that make sense? Right. So then here you can rearrange this and collect all the terms that depend on theta and theta squared, and then we'll call everything else constant because we only care about theta because that's what the distribution is defined for. And if you actually collect those terms, then you will see that this guy is Sn times theta n. Okay, and this guy is minus half of Sn. Okay, does that make sense? Okay, so you could do the same calculation in the other side, and you could do log likelihood n, and then it's the same formula. There's just one here, it's theta minus y, so sorry, it's y minus theta, but I'll just write as symmetric. There's no problem with that. And then we again do the same thing, right? We write down this is going to be, sorry, this is n plus 1. So this will be yn plus 1, and then this will be minus half. Okay? So you could see why things are added up now, because when you multiply, so like Pn times likelihood of n, if you did log of this, right, then this will be log of Pn plus log of likelihood of n, and then you just add these things together, right? So what I did is basically Sn theta n plus yn plus 1 and let me write plus minus half of Sn and minus half of theta squared. And we know because these parameters are valid, this is a Gaussian. So then we can write Pn plus 1 is exponential of these things. So it's simply, so then I'm going to call this to be Sn plus 1 minus half. I'm going to call this to be Sn plus 1 theta n plus 1. Does it make sense? And then I can put it in a Gaussian form to say it's going to be, Sn plus 1 theta minus theta n plus 1 squared, right? So I know that theta n plus 1 minus n plus 1 is what it is. Okay, so let me denote these guys. So I'm going to call, let me write a little bit more in detail. So this made sense, right? So, oh, I still have 2 minutes. This made sense. So let me just write the general one. These is all kind of unimportant things. You can learn it when you read the paper, but still notation is important. So I'm gonna write it down. Okay, maybe I'll write it down. So let's call, let's call Pn is exponential of lambda n times, so I will use transpose t theta. Oh, I didn't define any of this thing. Let me try to define it. So I'm going to try to write this guy as Sn. Oh boy. Sorry, uninteresting detail, but it still have to be done. So I can write it as an inner product like this, right? So then, I think this is the reason why nobody reads my papers. So, very annoying. But you know, what can you do? So I'm going to call this to be sufficient statistics T of theta, and I'm going to call this to be lambda n, a natural parameter, and I'm going to put transpose here. Okay, so essentially what I'm saying, okay, let me also do this for the other guy. So for this guy, you could say yn plus 1 and minus half times theta theta squared, and I'm going to call this guy as lambda tilde n. Okay. So why did I use tilde? It's a question. Maybe it becomes clear soon. But let me. So the posterior is written as exponential family of this. Okay, there's some constants, but I'm gonna ignore that for this presentation. And then, so I hope you're convinced about this. The likelihood is again written in the same exponential form, but I usually am using a tilde here. And the reason for using tilde is because it's not a distribution over theta, it's a distribution over y, right? So somehow it has flipped it, and I'm writing this as, it's not like normalizable with respect to theta, right? So that's why I'm using tilde. And it's very convenient because natural gradients are also used with tildes on top. So I was very happy when I found this same notation being used in 2 different communities that have been using this notation for very different reasons. But okay, so with this, you know that Pn plus 1 is now simply exponential of lambda n plus lambda tilde n transpose of T of theta. Okay, so whenever you take exponential family, you do multiplication of exponential family, you do addition. This is easy. Of course, you multiply exponential, you add their parameters. But the important point here is that the addition also leads to, old information, new information interpretation, which is what I'm kind of going at. You could call it reinterpretation, or you could be me and say this is how things work. Right? So that's what I'm kind of trying to claim with my work, that's what happens. Okay, so with that we can actually take a break. Maybe we meet in 5 minutes. Okay, so we've learned some things. We learned exponential family, and then when you multiply exponential family, they lead to addition of natural parameters, and there things are kind of happening automatically, is what we have seen so far. So let's go to the next part, and this is where I think we are moving closer to natural gradient. So far there is no notion of gradient in all of this, right? So what I actually showed you is that you can define all the new information by writing things recursively, right? And then you can interpret them as gradients, but you can also interpret them as natural parameters. And natural parameter space somehow it's a straight addition between things. There's no kind of weighing. But then when you go from this 2-dimensional space to 1-dimensional space, you basically start to get this kind of update where you have subtraction somehow. Okay. But there's no, so far we haven't written how things are additive, and that's what I want to do. So let me just write it again. So theta n plus 1 is theta n minus rho times the gradient, right, of ln plus 1. And then I have lambda n plus 1, which is equal to, lambda n plus some lambda tilde n, n plus, n. Then I want to show that somehow this lambda tilde n is also a gradient. Okay? Maybe I should. Let me write the gradient a little bit more clearly. So gradient is written as gradient of L, but it's at a theta equals theta n, right? So now let's try to think about what is the equivalent in the Bayesian setting. So let me try to. So let's think about like we think about arbitrary theta here, right? First, when we write the gradient, let me try to write. Gradient of L, it's evaluated at arbitrary theta, right? So let's think about gradients at an arbitrary lambda in a similar way. It's a gradient computed in a natural parameter at a natural parameter. So let's define. Sorry, I'm going to use Q for some reason. That'll become clear only later. But let's say that it's a distribution which has a natural parameter lambda. Okay. Is any objection to this? This is fine. I'm just going to call a distribution Q with a natural parameter lambda, and I just wrote Q lambda. And then what I'm going to try to do is, this is very weird, by the way, because it's not like usual gradient, so it doesn't make sense to you at first. So again, apologies for this, but there's no other way to do this. So now I'm going to try to write the. So first consider this, right, and then so take an arbitrary distribution. So arbitrary lambda. I don't even know if the spelling is right, but arbitrary lambda. Let's take that, and then let's try to take the expectation at that with respect to that arbitrary lambda of the log likelihood. So I did a lot of things here. Okay. So why? You don't know, but this is what the gradient's going to come out to be. So log likelihood, because we know likelihood is exponential family, right? And it's exponential family e to the power lambda tilde n plus 1 times t theta, if you remember, right? So when I take log, I get just this, right? And expectation of this is just expectation of that, right? So I can actually write this as lambda tilde n plus 1, sorry, transpose, and then expectation of q lambda of t of theta. Okay? So it's somehow, you can see now that it's somehow linear, like with respect to this quantity, that in exponential family, it's actually has a very deep meaning to this. So it's called expectation parameter. And I don't have time today to go into exponential family basics, but what actually happens here is that there are two spaces actually. Like there is a lambda space, and then there is also a mu space, and there is a one-to-one correspondence for a specific kind of exponential family, which is very large class, minimal exponential family. It's not important right now, but you can read the paper for which kind of exponential family lies in there. But there's a one-to-one correspondence between these two. So you can always write this exponential family e to the power lambda transpose theta in terms of mu, and this is kind of written in section 3. So there's some, so like I've defined these things there, like you can write exponential family in terms of mu, this one. And Arindam Banerjee is going to be actually here next week. So he actually did this beautiful stuff that you can write exponential family like it's lambda transpose t of theta, but you can also write exactly the same thing in terms of mu. So they're equivalent in the sense that everything that you write in terms of lambda, you can do in terms of mu, and lambda and mu are actually dual of each other. So they're, this is written here why it's a dual, because it's defined through what just Thomas talked about, this convex conjugates. So actually everything that Thomas talked about in that world of convexity has an equivalent in the exponential family. And this mapping is dense. Like every time you talk about Bregman divergence, there is an exponential family equivalent of that, which is KL divergence. So it's dense, meaning they're inseparable, right? So whenever you talk about convex duality, there will be something like that. And that's where we're kind of headed. So when we're projecting things to exponential family, we are somehow convexifying them in some sense. Okay. I'm very imprecise and very wrong in saying these things, but it makes you feel good when I say this, so let's just do it. Okay, so we're almost here, and now if I say that I'm gonna do gradient with respect to mu of this guy, right, then I will get lambda tilde n plus 1. It makes sense because it's just linear. So it seems almost like, oh, this is bullshit. I just took a linear thing and just took with respect to whatever. Sorry, I should actually say that this is evaluated at lambda equals, but this is not necessary here because lambda tilde n is just yn, right? So it doesn't depend on lambda. It's constant in this case. So it has no dependency, so you don't see that, but it'll show up later on, but fine. Actually, it's just like in the gradient descent case, right here, you did theta equals theta n, right? It's similarly, we do lambda equals lambda n. So it doesn't make any difference in this case because there was no dependencies on lambda n anyway. The information is completely independent because it's simply yn plus 1 and 1, right? It doesn't depend on theta n. So that's why it's obvious, but now we have it, right? We have it, and we can kind of write down the last things. Let's do it in blue. So let's write lambda n plus 1 equals lambda n, and then write down gradient of mu, and then do an expectation as an arbitrary exponential family of ln plus 1. Expectation is with respect to theta. I'm omitting that, but I hope that you catch that. And this is evaluated at lambda equals lambda n. Okay, so this is gradient, right? And then you can write the equivalent version and compare. Theta n plus 1 equals theta n plus 1 divided n plus 1 times negative of gradient with respect to theta, right, of n plus 1, and it's evaluated at theta equals theta n. Okay, so you could see that it's almost equivalent, right, except the fact that the gradient is outside here. It's actually has nothing to do with the loss. It's with respect to this lambda that's in the expectation, right? While here gradient is of the loss, so it seems very unnatural. Nobody likes it, and the scaling is not required in this case. It's just addition. So the scaling is not required. There's a scaling here, but there's no scaling. So you just can add these things because their scaling will appear automatically. Yes.
Maybe it's a dumb question, but so in the theta case, I mean, you update theta and you take the gradient with respect to theta, right? And in the lambda case, you update lambda, but you take the gradient with respect to mu. Is that like something that should be obvious why that happens? Or is that
yeah, it's not obvious right now, but when things depend on each other, then you will see this is what you're aiming for when the new data comes in, and the new data depends on, so you need to like iterate it multiple times. So you run Bayesian learning rule and it converges to this place. So then it's like the representative theorem that he was showing, like Thomas was showing, where alpha is dependent on theta star. So these natural gradients, they depend on lambda n plus 1 eventually. Yeah, it should be n plus 1. Yeah,
maybe as a follow-up. So I mean, the way you introduced it was very nice, right? You said we just want to add new information to old, and then that just pops out. And I guess in the literature, there's this other way that people often introduce natural gradients, and it's just say you want to be invariant to reparametrization, and then you get the Fisher information matrix and whatever. Like, how does that connect to this? Like, should it be like clear that this is the same thing, or what's?
It's entirely different, and I'm so happy you brought that up. It's completely different. So invariance, and I think Frank is here. Sorry, it's. Sorry, I was going to say bullshit, but now I'm hesitating. But I said it. Sorry, invariance is not bullshit. But the reason why people push natural gradients in practical places, saying, "Oh, it should be better because it's invariant," but then it's almost never the case. Right? So there's no such thing here. We're not talking about that, right? And
if I can just say one thing.
Okay.
Teacher our distance is invariant because natural gradient because of the step size.
Yes.
Not
not exactly. So maybe yeah.
I think there's likely another link as well, which is that you've got Fisher information is related to the attitude of information, which depends on your parameterization. So if you use natural gradients, you have the invariance with your Fisher, which should actually affect how things add up in terms of, it's a bit imprecise, but I suspect there is a link through additivity of Fisher information, and the Fisher information changes as you change your parameterization, and therefore there is I think a link through.
Yeah.
It should also be pointed out that normally when people talk about natural gradients, they're talking about in theta space because there's a Fisher information in theta because it's distributions for y. He's talking about natural gradients in the hyperparameter space, in the space.
Natural parameter space, yeah. So yeah, it's written in here in equation 19 because it was asked so many times that we stress that our use is more general. I was very happy to write more general. So actually, if you do this this stuff here, so I mean, there's another paper by people in Toronto whose title I disagree with because they say natural gradient as noisy something variational inference, but there's a different natural gradient they're talking about. They're talking about this natural gradient. So, okay, and they're saying this is equivalent to noisy variational inference. And I'm saying actually natural gradient variational inference is equivalent to natural gradient in the parameter space when you use Gaussian distribution. That should have been the title. That doesn't sell well, but it's a more correct thing to say. So I hope this makes sense. It's written like, have a look at that. I was going to say one more thing, but oh yeah, I was going to actually say that you can actually see why that thing is a special case is because this S. So what you will see soon, if you have time, that this guy will be the Hessian or Fisher in linear models, and then this thing becomes online, like it's just accumulation of Fisher. So this scaling, there will be a scaling somewhere, right? This scaling is essentially Fisher. You see that this grows with time, right? So it's as you learn, get more samples, the confidence increases, uncertainty decreases, and the step size becomes smaller and smaller. And so uncertainty plays a role. And this is just the principle why learning, information processing is inherently Bayesian, because it's just embedded in this framework. But this doesn't only work for Gaussian. It works for any exponential family. It's the same principle. Mixture is the same principle. So there's very little doubt after doing all of this stuff. And you can train GPT now with it. So I mean, it must be good. Okay. So, any more questions? Okay, so we're almost there at the Bayesian learning rule, right? So I'm going to do lots of cheating now because I don't like deriving it in. So let's say you were a person who didn't know what Bayesian inference is, right? I didn't do anything here, right? I said, oh, I should use two exponential family, multiply them together, and I get something where I get added, right? There's no Bayesian model as such. I mean, maybe this is the model, but there's no prior, right? And it didn't have to go through any of that. I didn't even have to go to variational objective or anything, right? So it's the same thing. I can actually write all of these things down from first principle, without even thinking about the model or the objective, but I could just think about the algorithm. When I run the algorithm, it does something, it converges somewhere, so it must be optimizing something, and then you can figure it out in this reverse way. So what are good algorithms optimizing? Well, I think it's something Bayesian, because you will see its role of entropy. So I'm very excited about talking about this now. I hope I can finish this and I can show some linear regression, which is also exciting sometimes. So let's say theta n, right? So theta n is actually, let's go back to thinking about sample mean. And let's say we didn't know the objective of sample mean, right? How would you figure out the objective of this? Okay, can anybody think about it? What's the objective it's optimizing? Sorry, what? Yeah, you know the answer, so you say it, but let's say you didn't know it.
Subtract theta n to make it equal to 0.
God damn it, I hate you. You know all the answers. Okay, that's exactly true, but why? How did you come up with that?
Because we want to minimize something, right?
Yeah.
So we want something to be equal to 0.
Yes, it's correct. Actually, the DNN to GP paper, Alex, if you remember, that's how we derive Laplace. It's a beautiful trick. I love it. So essentially, what he's saying. Sorry, I forgot your name. What he's saying is that you put 0 here and you subtract theta n here. Is this correct? Because I think it's equivalent, what I just did, because it's divided by 1 by n, right? So now I know that it's the fixed point of something, right? And I can think about what it's fixed point of, but I can also like think about an algorithm that converges to this fixed point, right? So I can actually try to write down the algorithm to say, oh, let me add theta on both sides of it, because that doesn't change anything. Or let me multiply by a step size, and yeah, I don't know why I kept the n. And let's just add theta on the both side. Sorry, and then make it like an algorithm like. Sorry, I hope you get it. Like this is t plus 1 t, and then I am optimizing at t. And you can sort of see like this converges to that place, right? It's just a different way to write it, right? I want to converge to the solution. This is the bad solution, right? I have all the data at once, and I can rewrite this in this way. But we could do the same thing with Bayesian learning rule, right? So we can start with the solution, and we know the solution is lambda n equals lambda. So I'm doing n now because I want to, I don't know why I'm doing n. But sorry, I might have messed up with n and n minus 1, but let me just use, and you know that these are somehow n minus 1. Don't worry about this too much. But you know that this is the fixed point that I wrote a little bit before. I mean, maybe I can just write n minus 1, fine. Okay, and then I know that lambda n minus 1 also has the same thing, right? So I could write like this, right? And then I can continue in this way, and I'll get a sum over all i's until n. Does that make sense? So I basically just unrolled it. Actually, in online learning, this is called lazy training. But we are actually trying to write a representative theorem in terms of dual variable. That's what's going on. These lambda tildes are somehow natural gradients. So it's written like that. And then you can actually derive Bayesian learning rule from here. Well, what we call Bayesian learning rule is that, oh, I want to get to the fixed point of this. So I do the same thing. I do 0. I do lambda n, right? And then I will add and subtract. Well, I could add subtract, but I will add this to be t. But basically at a step size, 0 doesn't do anything. And sorry, minus n, okay? And because it's an iteration, sorry, I'm going to do something very bad. I'm going to evaluate that lambda tilde at that lambda t. So you were asking this before, Vincent, but basically that's kind of what I was saying. So this is going to be natural gradient with respect to mu of expectation of q of some kind of loss at ith time, and then I'm going to evaluate it at tth thing. So it depends on I, right? It depends on I and it depends on t. So two of those things. And then I have an iteration, and I call this Bayesian learning rule. Okay, this is Bayesian learning rule. So now you know. Go cite me a lot. Okay, so so you see, like, you're just trying to optimize this fixed solution where things are written in terms of sums of all these lambda tilde. But then you can start to think about what it optimizes, right? Like, so you can actually go in here and you say, oh, what does this optimize? Oh, I know. It optimizes the gradient of this guy, right? That's how you can, it's a fixed point of this thing. But you can write very similar things here, right? Because, so in the similar way, somehow it should be, this should be maybe let me write it. So you can actually kind of say that this condition is equivalent to somehow gradient with respect to mu of expectation of q of li, sum over all I, minus something that gives me gradient of lambda n. And that gradient has to be 0. Something like that. Huh? Sorry, maybe so it's a gradient of mu and something here such that I will get lambda, right? Lambda n. Does that make sense? No? Sorry, it should do slower. Okay, let me write the whole thing. So, sorry, what I'm basically saying, that what does it optimize? It's somehow at the fixed point, it should be gradient of, sorry, even simpler. At the fixed point, this is true, right? No. So this is basically what I'm saying, that it is, so rho doesn't matter at a fixed point, but it's, we know that this is gradient with respect to mu. Lambda n plus 1, because we converge there, minus lambda n. Does this make sense? It's just, I just rewrote it. Sorry, I wrote something wrong.
No, it's just one question. So basically, like in that line before, you somehow always kind of you do this unrolling, right? Basically, like lambda n, you unroll it. But then you have all the tilde terms, but then there should always be like lambda 0, right? You assume lambda 0 to be 0 or.
Lambda 0 to be lambda tilde 0. How about that? Or lambda, first iteration is just lambda tilde 1. Is that good? Yeah, that's called prior. I'm avoiding that question. It could be 0 in this case. Yeah, or yeah, it could be something that you initialize your algorithm with. It's fine. Yeah. That's your prior. It's okay. Does this make sense to people? Yeah.
Okay, so then I'm basically saying that I'm actually trying to minimize something where this is expectation of Li, so I sum over I, n, and then I write min. But I need something here that's, sorry, plus, something whose gradient is lambda n. Natural gradient, like gradient with respect to mu is lambda n. Actually, there's only one thing. What is it? People know? Nobody knows. This is very weird way to write it. Is the entropy of q lambda. Okay? So I think this point seems completely irrelevant, but please stick with me because this will show up in RMS prop. Okay, so RMS prop has an entropy term. This is very important. Actually, it's a fact that gradient of mu of this is equal to lambda. The opposite is not true. If you try to write it with respect to lambda, it's not easy. and I think maybe Frank knows a lot of tricks about this, why this happens, but entropy is just not symmetric. It's just simpler when you take derivative with respect to mu, but it's not simple. Actually, I know the reason. Sorry, maybe Zelda will appreciate this. I'm talking to each of you individually and I lose everybody. But it's because it's a star of lambda. It's a star of mu. It's actually convex. So, okay, let me just give a spill. People know this, they will know. Bregman divergence, you have a generating function, convex function that generates Bregman divergence, right? In exponential family, that generating function is a log partition function. Okay, it's the same quantity. So that's why there's one-to-one between exponential family and Bregman divergence. So generating function is a log partition function. Okay, what's looking up? Let's just write it down. When I said e to the power lambda transpose t theta, I hid something that's the partition function. This is the normalizing constant of the distribution. I'll finish and I'll let you ask. But this is log partition function, and this also appears in Bregman divergence at the bottom. And it's the same quantity actually, okay? And entropy is actually a star in the dual space. Okay, this is entropy of Q lambda, where Q is this. Oh, I actually gave a tutorial on exponential family just right now. That's all you need to know. Okay, exponential family written like this: the partition function of the normalizing constant is the convex function for the Bregman divergence. So there's always, this is also KL. So how do you measure distance between distribution is equivalent to specifying the distribution? It's the same thing. There's lots of deep works here, and Frank will talk about some things tomorrow. Really fascinating stuff, right? Duality of information geometry. Who would have guessed? Sample B. And then this is entropy, it sits in the dual space. So that's why if you take the gradient with respect to me, it's simple, but the other way is not true. So that's why this objective actually makes sense. And this objective, if you don't realize it right now, this is called variational inference in some books. So you could actually add a prior, maybe you could do the sum from 2 and put the 1 in here, and you can write this as KL between that and the first guy, something like that. I'm not going into detail, but that's how, so Bayesians, it depends on where you start. But it doesn't have to be that way. You can start somewhere, like whatever deep learning people are doing. You initialize things some way, and that's your prior. And from there you run things. But the entropy is kind of there in the update. When you're doing this addition, right? You add all the gradients and you add them, and it becomes the natural parameter. Did I actually make a mistake somewhere? I have made a mistake somewhere. Yeah, this is not correct.
On the top, I guess it should be.
And place 1? No. Yeah?
No, on the top of the page it should be negative and
yes. Top of the page? Yeah. Thank you, yeah. Yes, sorry about that. Again, roughly correct. So here there's 0, right? But in this case, you assign these cumulative things to lambda n. So the left-hand side is actually not 0, it's lambda n. But actually, if you rearrange that, you will recover this equation as you've seen it, right? If you go from lambda space to the mean parameter, you will get this solution. If that didn't make sense to you, maybe you need to do it by yourself. Don't have time to talk about this. But is there any question, or did I lose everybody?
Can you summarize again what is the Bayesian learning rule?
Damn it. I'm excited, come on. I missed the point. Yeah, that's the Bayesian learning rule. Okay, I wrote it here. So yeah, that's Bayesian learning rule. Basically, at every step, you sorry, this should be T, sorry. Ah, that's the problem. Yeah, because lambda n is the solution where you want to converge. So this has to be, as it keeps updating, at fixed point this becomes equal to that, and they cancel. And then this becomes equal to this. Okay? So that's, and lambda t converges to lambda n. Maybe let me just say, as you run this, lambda t will converge to lambda n. So sorry about the notation, but lambda n is the bad solution, and lambda t is the iteration that converges to lambda n. So you run this. I mean, in other words, you can write the same equation as lambda t plus 1 minus rho lambda t plus rho times the sum over natural gradient, right? And now that we have 10 minutes, you can, let's derive RMS prop, shall we? I'm going to skip the linear regression part. No, we cannot derive it. I'll have to give you, I have to say like something, yeah, I don't know. We can have discussion, or I could derive RMS prop, I don't know. Is this clear? This is good, right? We can call this BLR. It's in, if you go in the paper, it's kind of, so it's, yeah, this version is kind of written here in a more accurate way in this equation 6. But the original version that's written in the paper, it's written with the natural gradients like this. You know, it's not. So it's written. This is the one that I derived at the bottom here, like this one. Like this one is same as in the paper. Equation 3. Write this down. Equation 3, and this one is equation 6, but they are kind of same, almost same equation. Okay. Yes.
The version you have here, is this well defined outside of a conjugate case, and then you get lambda tilde, whereas the version in your paper is
that's how you get it. So this was, sorry, I didn't say it. I didn't say it, maybe I just, yeah. I've done this for many years, so I apologize. But you can write the loss to be anything, and it will kind of naturally, you can see this as a natural parameter, that lambda tilde.
So one way to think about this is that the thing in the red box is, that's exactly as you update it. And then, but it only applies in the conjugate case. To get outside the conjugate case, you replace lambda tilde with the gradient in the level up.
That's another way to think about it, yeah. But they're gradient even in the conjugate case.
Well, sure.
Yeah. So they're always gradients.
Yeah, I'm just saying that the top line applies only in the conjugate case, and the line below it applies in the general case.
The line like this?
Yeah.
I'm not trying to do that. That's mischaracterization. But yeah, like I'm defining lambda tilde. I had written it before, but then I erased it. But I'm defining lambda tilde IT to be this way, and then that's it. Right. I had written it, but then I wanted to explain, and I had removed. So let me just write it one more time. So I think I defined it somewhere, no? Yeah, I wrote it somewhere. Yeah, I wrote it here, for example. So let me rewrite it. So I'm just basically saying Bayesian learning rule says I don't care if you're conjugate or non-conjugate, but I can always apply this gradient to anything. And then when I do, in conjugate case, it's just one step. So you just get lambda tilde and you converge. So that's why it will, yeah.
I think this is the projection step. This is the projection step.
It is projection step, but people hate the word projection. I just learned today.
The projection is a vector thing.
Yeah. I mean, I think I don't want to talk about projection in the iteration because the notion of old and new is not yet settled. When you converge, then you kind of know. So if you're here and you say this is a natural gradient, right? This natural gradient plus the old natural parameter. So the old natural parameter is old, and then this natural gradient is the new information. Then that makes sense to me. And that's easy. You just add things. So at convergence, at BLR, you'll always see this. So actually, it was kind of such a simple thing that I had to insist in the paper to. So there's you will see this line here that is written. That it's not a matter of choice that you have natural gradients. Whenever you take the converging point, you in the solution always appear natural gradient. Think of it like when you're doing linear regression, you can at the convergence it's a Newton step. It has a matrix inversion, like system solve, like linear equation solving. You can use gradient descent to solve it. It doesn't mean that you're not solving a system. I mean, maybe you do SGD and you pretend that you're not solving a system, but you're actually solving a system. So it's the same kind of thing. You can use black box variational inference or whatever tool you want to do, gradient descent on lambda space. In the end, it will still compute natural gradients because the solution is that. This is important. Natural gradients are inherently present in all solutions of that objective too. And my hunch is that it's always present, this kind of duality. This computed in a different space, this computed in the natural parameter, another space, where entropy is kind of somehow easy to compute. That's the dual space. So that has to be the case always.
But then you see guys that the solution is always unique.
No, it doesn't. No, this is a fixed point, so it doesn't imply that. So for exact Bayes, there's always a unique posterior, and you can show that the Bayesian objective that I wrote with entropy, it always has a unique solution. It's strongly convex in some sense. But when you use restrictions, then it's no longer the case. So when you say it's only Gaussian or exponential family, then it's not convex. So then I don't know. Yeah, that one sucks.
I see that because in the choice of the algorithm will implies that you might converge in a different way.
Choice of the algorithm will imply that we will converge to a different solution. It's possible, yes. So I mean, I think doing better, natural gradient should be better, but I don't have a proof of that. I mean, we have some results on like training large models. It just works. It works. Other methods don't even work. So maybe that's the reason, but I cannot claim it. Yes.
I have a short question on something that I really never understood. Is when you show the VI, the alpha objective, we have the KL divergence, and then the Bayesian learning rule, we have the entropy. But then, like, mathematicians usually prefer the KL divergence instead of the entropy.
Yeah,
and
KL.
Sometimes we think about the KL as the more like original, like the more primal thing. So yeah.
Look, I think KL is nice because when you have a prior, you can, so this maybe non-Bayesians should this. When you have a prior, then you can assure that there's always a solution to this. But when you don't have a prior, then this may not be defined. Makes sense. I think Sam stepped out, but in Gaussian homotopy, I'm sure they have this. Like, I think in his own paper, when variance is very high, then the objective is unbounded. You can actually show that. And he actually wrote a proof on this in 2015. But if he was Bayesian, he won't have to write that proof. Okay. I wanted to show you very nice things in linear regression and RMS prop, and it all makes sense. But let me just kind of say something very quickly. What happens in RMS prop is that you really, maybe I could write it here because I've already written it, but what you do is you start writing this kind of thing, like theta t plus 1, and you said this is st theta t, right? And you said this is st, st, and then, st plus 1 and st. This is like, this is lambda t, and lambda t plus 1, and this is lambda t, right? And what actually happens in RMS prop, or Newton's method, is that you write natural gradients here. This comes out to be the Hessian. Let's just do one example, not batch, but let's just do one example, Hessian. And this turns out to be, lambda tilde, is turned out to be gradient plus the Hessian times theta t. Okay? I mean, you can see in the BLR paper, this is actually shown in, let me write down the equation. I'll post the annotated version. So this equation is actually proven, and you can check it in the paper. So write equation 10. So once you have this, what you do is basically you actually it's so simple that you realize that if you actually moved this guy here, let me do it, it's very satisfying. If I move that guy, sorry, there's 1 minus rho, there's 1 minus rho, so there's 1 minus rho here, and then I put HIT times rho times theta t minus rho GIT. Do you see, it's actually same as the sample mean case. I don't know if you see it already, but this is the ST plus 1. So then you do the same thing, you know, you can cancel this, and the ST plus 1 shows up here. So you get an algorithm that we call something like RMS prop, where you have theta t plus 1, theta t minus rho times st plus 1 times GIT. So when you're in the lambda space, it's just addition, right? But when you're in the, go from the natural parameter to the theta and the precision space, then you start to see Newton-like things. So this is covariance. So I'll end this tutorial. Oh wow, I should have ended 1 minute ago. End this tutorial by saying the covariance modifies the step size. It actually, and then this is the new information somehow. And actually you can show that this is also projection. So it's all good. Everything works out. But if you did gradient descent, then you will be missing this part, right? So that's not quite right. So it's kind of worse than that. And anyway, I won't get into that. But my point is that if you did addition in this space, it naturally leads to this kind of update that we use. This is, all of this stuff is written in the BLR paper. Thanks for listening, I'm done.
So let's go for this last talk for the day. So we will have Matt Jones, who's a professor at the University of Colorado Boulder in the Department of Psychology and Neuroscience, yes. Mainly working on human learning and knowledge representation, and he will talk about BONG.
Yeah, so this is, I'm glad I got moved to this spot in the talk, in the schedule, because I'm going to be building pretty directly on what MT just did. With a focus on online learning. So we're thinking about a setting where data are received sequentially, you get one observation per time step, inputs X, observations Y. And we're mainly interested, I'm not going to focus on this today, but we're mainly interested in non-stationary settings where there's some shift in over time in the marginal distribution of X and the conditional distribution of Y. And so the model has to adapt to changes in the environment. So the model, we think about neural networks, there's, so you have some predictive model, in the same setup that everyone else has had for the most part, where you've got some weights, and we have the predictive distribution from the model, which is some function of the inputs and the weights, and that gives some probability distribution over Y. And we just shorthand it like this, so we don't have to have X's everywhere. And in online learning, what we're usually interested in is the agent's ability to interact in real time. So the target here is what we call preferential evaluation, which is just one step ahead prediction of the next item in the sequence. A common framework for doing online learning, from a Bayesian standpoint at least, is state space models, where you assume that there's some true latent state, theta, that evolves over time according to some dynamics. Then you also have some observation models, so the graphical model looks like this. And then from a Bayesian standpoint, what you want to do is Bayesian filtering, where you maintain a posterior over the current state as a function of all previous data. So Bayesian filtering involves two steps. There's a predict step where you go from the posterior on theta t, given all the prior data up to t minus 1. The posterior on theta t minus 1, given all that prior data, and you push it through the dynamics, as shown here, to get a iterative prior on the next step. And then there's an update step where you observe yt, and you get a posterior on theta t using Bayes' rule. Just to get us all grounded, the most common example of Bayesian filtering is the Kalman filter, where the dynamics are linear and Gaussian, and so are the observations. In this case, so you've got, the cartoon here is that there's some latent state that's evolving over time according to some random walk. You have a series of observations, and then you have your posterior mean estimates after each observation. And the predict and update steps can be computed in closed form in this case. So your prior at time t is based on, prior on time t. Everything's going to be Gaussian. Your belief state is always Gaussian. Your prior at time t is derived from the posterior at time t minus 1 just by pushing through the dynamics. So F and Q are define the dynamics going from theta t minus 1 to t. And then the update step after you observe yt is just Bayes' rule. And if we think in terms of, I can start tying to MT's talk here, the sigma inverse is one of the natural parameters, and you're just adding natural parameters. So there's the natural parameter from the prior, and this is basically the Fisher information, which is the contribution of the natural parameter that comes from the observation. And the same thing happens with the mean if you reframe things in terms of natural parameters, which is where we're heading. So that's one example of Bayesian filtering. And it's the simplest one, and it's one where you can have closed form updates.
I think the sigma t ht transpose rt, the preconditioner, right? That's like that's the st.
Yeah. So actually, the sigma t here is the preconditioner, and the rest of it, everything from the HR inverse times the error here, that's all the gradient. Yeah. And we'll see that same form recur here. Okay. All right, so that's the setup for online learning, Bayesian filtering. Now just a quick review, we've seen this already, but variational Bayes. The idea is that instead of doing exact Bayesian inference, you're doing inference within some parametric family, some variational family parameterized by psi here. And the goal is to minimize the KL divergence of your approximate posterior, Q psi, from the true posterior, which is given by everything on the right side here. So you have your prior times your likelihood, standard Bayes rule update. The one nice thing about VI that I think everyone knows is that the normalization term drops out of this, because minimizing, anyway, it just contributes a constant to the KL divergence that doesn't depend on psi.
so we don't have to normalize. So the optimal VI posterior is given by minimizing this VI loss, which is the negative elbow, right? And the negative elbow decomposes into two terms. If you just rearrange the this KL expression here, it decomposes into a sum of expected negative log likelihood, which is a fit term, and regularization to the prior, KL divergence from the prior. So that's what VI does, and this decomposition is going to be important too. Now let's put things together, talk about variational inference in the context of online learning. Okay? So instead of having a single prior and some batch update, as on the previous slide, we're now talking about carrying forward an approximate prior from the previous time step and doing variational inference to update it to the next time step. Right? So we have a prior coming from the previous time step, which I'm going to denote as based on psi t given t minus 1, which is just notation for, that's the belief state about theta t given all the data up to t minus 1. And that once again just comes from pushing the posterior after step t minus 1 through the dynamics. Right? That's not really going to be the focus here. The focus here will be on the update step. For the update step, what we do is we approximate the posterior, we approximate the exact Bayesian posterior by what you would get from updating with the approximate prior. So you carry this approximate prior here into the update step, and then you approximate this line using VB, right? So that the approximate prior at the end of the update is the minimizer of this online VI loss, which now just by using the same reasoning as I derived on the previous slide, can be decomposed into the expected log likelihood of just the current observation plus a KL regularizer to the prior at the beginning of just the current time step. All right, so this is still not tractable because of this expectation term. So if in the context of neural networks, for example, so I've rewritten the online loss as just the sum of these two terms. This is this Roman L here is just the expected negative log likelihood, and then we have the regularization term. So the expected negative log likelihood is not tractable because this is some complex nonlinear function that you're trying to integrate over. Even if this is a simple variational distribution like a Gaussian, you still can't integrate it. So you need some sort of methods for approximate VI. And so I'll talk about this basically just related work background. Existing methods for doing this approximation. So first off, this is not really an approximation, but you can compute the exact fixed point of the you can compute the exact minimizer of this online variational loss by computing a fixed point. If you take the if you set the gradient to 0, then you get this expression, and this uses the same kinds of mirror descent tricks that MT just talked about, where you switch over from the natural parameters. I should have introduced this first. So if we assume that the variational family is an exponential one, and psi are the natural parameters of that exponential family, and then I introduce, sorry for the different notation, but I'm using psi as the natural parameters, rho as the dual parameters, then you get this implicit update here, where the new, the exact optimal posterior natural parameters are given by a gradient descent update where the gradient is with respect to the dual parameters. So this is the same as a natural gradient with respect to psi. I forget whether you said that in your talk.
Mu?
Yeah, right. So my rho is your mu, my psi is your lambda. Yeah, right. But the point is that this term here, so this is the gradient with respect to the dual parameters, and that's the same as the natural gradient with respect to the natural parameters, which was, I think you mentioned, but yeah, okay. Right. Yeah, I mean there's a lot in there, right? Yeah. Anyway, so you can drive it, but this is the exact solution, but this is implicit because we're evaluating the gradient at the solution, so you can't compute it directly. but it'll be relevant. This can be done, for example, for the case of a Gaussian variational approximation. So Lambert et al. Had this paper they called recursive variational Gaussian approximation, which is Bayesian filtering for the Gaussian case, where the variational family is Gaussian. No assumptions about the likelihood, but the variational family is Gaussian. And then you get these updates, which look a lot like the Kalman filter and look a lot like equations that MT showed as well, where you're updating the mean based on an expectation of the gradient, where the expectation is taken over the posterior, and it's preconditioned by the variance. And then the precision has a nice update where you're basically adding precisions, and what you're doing is you're adding the negative expected Hessian. So that's one example of how you can, what the exact update looks like. But again, these are implicit updates. You can't actually directly compute this, because you need to know the posterior in order to compute the posterior. Okay, other approaches are iterative ones, where we take the VI loss and do gradient descent on it and converge to the optimum, right? So if you just take script L as a loss function, we can just optimize it using gradient descent. So the first well-known paper, I don't know if it was actually the first, to do this is the Bayes by backprop, the BBB approach, which just does gradient descent on the VI loss. And then one way to cast BLR is that you're just doing natural gradient descent on the very same loss instead of gradient descent. And you get this update here, which is basically the same thing that we just saw with MT's talk, it's just with different notation. But the new natural parameters are equal to the old natural parameters plus a natural gradient of the VI loss. And this VI loss decomposes in this way, but you can decompose it in the other way as well, where the entropy shows up instead of the KL regularized. Yeah.
What was the sub-indices on sine and rho mean?
Yes, thanks. So these BBB and BLR, as I'm presenting them here, are batch methods. So whereas what I'm talking about in the top half of the slide is an online method. So I'm using T to indicate actual time for the agent, where you consume a series of observations, where I'm using I for iterations of the algorithm. And I'm going to combine these in a moment. But for now, these are batch methods, and you're just iterations of gradient descent.
We just switched that part completely. My n was your t,
yeah,
and my I is your.
Right. So in some ways, it was really fantastic that I was at this point in the schedule conceptually. In other ways, it's disastrous because the notation is clashing everywhere. Yep. Okay. So we have these methods. Iterative optimization methods, just optimizing the VI loss. And then finally, there's a family of methods based on approximating the likelihood. So instead of using the exact likelihood, P of y given f of theta, which you're getting out of your neural network, we can approximate that in various ways, basically by linearizing it. So classic methods, these date back to the 1960s, but these references are the first ones, I think, to apply them in machine learning and neural networks. You take whatever function the neural network is computing, and you linearize it based so you just do a first order Taylor approximation at the prior mean. That's what this F bar is, and where capital F is the Jacobian. And then you have if your likelihood were Gaussian to begin with, but it's a Gaussian function of the output of some highly nonlinear function, you can just linearize that function, and then you get something that conforms to the Kalman filter, and you get a closed form update based on this. Okay? So this thing on the right-hand side, once you approximate the likelihood in this way, you get an exact closed form update. In cases where your likelihood's not even Gaussian to begin with, where you have just some general likelihood, you can do the same thing, where you again approximate with a Gaussian, where the mean is based on the mean of Gaussian is just the expectation of y given the output of your model, and linearized. So we just have this is again a first order Taylor approximation based at the prior mean, and then you take the variance, take a fixed variance based at the prior mean as well. right? So this is this conditional moments EKF that was proposed several years ago. And this once again gives you an exact closed form update, right? So rather than approximating the loss, we can approximate the likelihood. And then once we do that, we get a loss that can be solved in closed form. And finally, another way to approximate the likelihood, essentially, is rather than integrating over the variational family, we can just do a plug-in or a delta method, right? So we just substitute the prior mean here and don't integrate over all values of theta. We just directly evaluate the value of the log likelihood at the prior mean, so that this term here becomes this term here, right? And there's, I don't want to get into the technical details, it'll go away in a little bit, where I take the expectation parameter from my belief state as the prime.
You mean mean?
What's that?
Mean.
Mean.
Like not the expectation parameter. Like.
Well, that's the technical thing I want to skip over. So in the simple case, right? So here's the case where this actually works. Okay, if your variational family is a Gaussian with a fixed covariance, then the expectation parameter is the mean. The expectation parameter and the expectation of theta are the same thing. Okay. More generally, if you have a curved exponential family, then rho is not a valid value for theta. Right? It's sort of a hallucination, in a sense. I'm going to talk about different plug-in approximations in a little while that work more generally, but again, this is just background. All right, so yeah, the method I'm going to propose here is sort of draws on all of these different ideas. Right? We can derive it as in different ways from using approximate likelihoods, either through linearizing or through using this delta method. And I'm going to prove a theorem, or going to present a theorem in a little bit that shows that they actually give the same result. And then also going to show how we can use these iterative methods in a more efficient way than existing work. Okay, and that is our method, Bayesian online natural gradient. The way we derive BONG is starting from an online version of BLR, okay? Which is in fact the version that you present. Well, no, it's not. No, because you did a batch version, but you were going to do the online version. So if we're doing an online version of BLR, the idea would be that we would take the online VI loss, which again decomposes as the expected log likelihood of the current observation, or the negative, flip all the signs around, put a minus sign here, so you have the expected negative log likelihood plus a KL divergence from the prior that was carried over from the previous step, okay? So you have a fit term and you have a regularization to the prior. And what we do is natural gradient descent on that loss and use that to update the natural parameters of the belief state. Our insight, and this is sort of the core idea, this is one of two core ideas defining our method, is that instead of having this regularization term, where we explicitly regularize to the prior state, we can implicitly regularize with a truncated update. So this method here, and I said in response to your question a few minutes ago that I'm going to combine the two time indices. Notice what's happening here is that at every time step, the agent's going through the world and experiencing a series of observations indexed by t. At every time step, we have to do an inner loop where we converge to the optimum of the VI loss, and that's indexed by I. So we, at the beginning, when I equals 0, we set psi t comma 0 to be the prior, which is actually the thing in red right here. We start there, and then we iterate this natural gradient descent until we converge. Instead of iterating with some learning rate, what we propose to do is do a single gradient step, single natural gradient step, and at the same time drop the explicit regularizer. Okay, so two changes. So this KL term has disappeared, and the alpha has disappeared. And those are actually the only two changes from the BLR equation to the BONG equation. And these two changes work in concert, right? So instead of explicitly regularizing to the prior, we do truncated, we do regularization through truncated updating, where we start at the prior, right? This is our starting point is the prior, and we just do a single step rather than going all the way to convergence. And that's an implicit regularization. By the way, we just realized this yesterday. It should have been more obvious. But this is, you can actually get this as a special case of BLR, where your number of iterations is just one. You do a single iteration, and you set your learning rate to 1. And the reason for that is on the first step of BLR, this KL term will be 0, obviously, because and moreover, the gradient of the KL is 0 because it's smooth. So on the very first step of BLR, actually the regularization term doesn't contribute. Yeah.
Is there a difference between psi sub t comma I and psi sub t dash vertical bar?
Yes. So for BONG, there is no I because we just have a single update per time step, right? So you can say I equals 1. But we don't put that in there. So psi t is the posterior belief state, and when we run BLR to convergence, you have to. I use capital I for the number of iterations, but you run it through capital I iterations, and then psi of t comma capital I will be your final belief state, and that's going to be psi t. That's the thing that you carry forward to the next step. The thing that you bring from the previous step is psi t given t minus 1, right? So that's the notation there is just indicating that it's conditional. So it's your belief state about the current value of theta, theta t. Again, there's a dynamics here. So theta t and theta t minus 1 are not necessarily the same thing. So it's your belief state about theta t conditioned on the data up through t minus 1. That's what the thing shown in red here is. Does that make sense? So let me show the diagram. Actually, this may be helpful. So what BLR does is it starts at the prior belief, online BLR, which I'm calling OBLR. It starts at the prior belief, which is a thing that was carried over from step t minus 1, and it does a series of updates, natural gradient updates, and after it decides it's done by whatever criterion, it says, okay, this is my posterior psi t, and it carries that over to the next step. What BONG does is it starts from the same prior and it does a single update and calls it done, right? That single update differs from the BLR update in 2 ways. One, it doesn't have the KL divergence term. So each one of these purple arrows here is not just improving on the fit to the current observation, the expected negative log likelihood, but it's also being pulled back towards psi t minus 1, it's being pulled back to it because of this KL divergence term. Go ahead.
So, like, maybe I'm a bit lost, but I'm wondering, like, what is the thing we're trying to solve? Is it like rapid adaptation? Because, like, the top thing that also reminds me of variational continuum learning, which is something that
right. Yeah.
And like, I've never really understood the argument. Like, if I think of like a covariate shift and I just put something really stupid on it, like a sinusoidal perturbation that just like changes back and forth.
Right.
It seems like this thing is just constantly going to adapt like in one direction and then back into the other, and in one direction back into the other. Like, there's nothing stopping, right?
Yeah,
is that true? Or
that's kind of, well, if I'm understanding you, I mean, that's kind of what we want. I mean, think back to the Kalman filter, right? So the true latent state is evolving over time. Now you said a sinusoid, but we could put whatever dynamics we wanted on here. In order to get psi t minus 1 from psi t minus 1, you just have to push through whatever your dynamics model happens to be, right? So but it's just a generalization of the Kalman filter where you have some kind of tracking problem. There's a latent state that's changing over time, and you get noisy observations about that state.
I guess that's why I was asking if that's what we want, because I would have intuitively thought like maybe we build a core set and then we kind of just have memory of the past. You don't need to adapt to it again. You just remember tracking the future and the past. Yeah, that's right. So that's actually different. So a core set approach, and it reflects a view of continual learning where the environment is actually, well, I was going to say the environment is stationary. The environment isn't stationary, but P of y given x is stationary. Right? So maybe you have covariate shift,
right? Maybe the task is changing. So you're learning over in this region of X space, and you learn over in this region of X space. And what you want to do is hold on to, this is what you're saying, you want to hold on to past XY pairs from the region that you're not currently in. That works in a case where P of Y given X is constant, right? Where the task doesn't change. You're being trained in different regions of the space. By task, you're thinking of multiple tasks, but I can still say, well, that's just a union. I can say one task is a union of multiple tasks.
No, I was thinking of one task, right?
Yeah, oh, okay.
The same sort of task.
Okay.
It's just like you covariate shift. Like you do cancer detection, you do it here.
Well, sure. Okay, yeah, fine. So, okay, right. So we're saying, we're in agreement. Covariate, right. Yeah, state space model approaches are not necessarily so useful for covariate shift. They're more useful for concept shift, where the mapping from X to Y is changing with time.
I see, yeah. I guess this is more common with VCL than this.
Actually, not sure about my question, but usually when you solve the regularized loss, when you have a loss classifier, which is in this case, so if you calculate the, let's say, implicit solution, by kind of like solving it exactly, you usually get like some sort of precondition update, right?
Yeah, like the implicit, like this kind of implicit solution here, right?
Yeah, implicit, my point is that the gradient is calculated in the future.
Yeah, right.
So I'm just wondering if you assume that you're, maybe like going back to the equation that you have, future stuff. So yeah, if you assume that your step size is, your delta is small, maybe you can solve the top equation in closed form, because you can do a second order Taylor expansion of the variable divergence.
Sure.
Plus the loss. So my point is that what I was expecting to see on the bottom equation is some sort of maybe preconditioned gradient. So it's like psi t minus 1 plus some precondition inverse times the gradient. But I'm not sure. I'm just basically. Yeah,
it seems to me that's require. That's going to be a second order method, because you're talking about how does the gradient change as a function. So you're going to need the Hessian of the model at that point, right? Isn't that going to be expensive?
There is Hessian happening because of the natural gradient, right? So like the Jacobian is basically this second order.
So you don't have to do any second order of the KL. Sorry to steal it.
Right. Yeah.
But KL is already tractable.
Yeah, KL is tractable because it's exponential family.
Yeah.
Yep.
And actually, the NLL is also tractable, because at least in the exponential family case, because you can just directly do the gradient with respect to rho, right? The natural gradient.
So there is a scaling there in front of the gradient.
Yeah, true. I guess it naturally happens with the bottom of K because of the. So I was thinking more like if you could solve the top equation, or like a simple case, if you could solve the top equation, what would you see? Is it like something very different than the bottom one, or the approximation is actually good?
Well, let me give you this. So the one case where you can solve the top equation is the conjugate case, and that's what I'm going to show you in the next slide. Is that then they end up being equal. So for justifications for a method, one of them is sort of the simple version of what you're saying, or it's the thing that you want to improve on. So this is the BONG update here, and this is the implicit update. This is the exact modulo the VI thing. This is the optimal VI update, and they differ precisely in that this is the explicit version where you're calculating the gradient at the prior, and the thing that you want to do is calculate it at the posterior. Right. Yeah. Right. So one way to think about what we're doing is we're saying, okay, here's what we want to do. We can't do this, so let's just do this instead.
Right. Exactly. Yeah.
But cool. Okay. But then the other thing is that in the conjugate case, they end up being the same thing. It turns out. So I'm going to show that on the next slide. So that's our first theorem, and it's pretty close to stuff that MT showed as well. But this BONG update turns out to be the exact Bayesian update. And then before I show that, let me just say this. here is that what we're going to end up with is a framework that derives a whole bunch of existing methods, and so that's another. That's I think another reason to be interested in this update rule. So here's our theorem. Take a case where not only is the variational family an exponential one, but the likelihood is also an exponential family. And the two exponentials or families are related in that one is the conjugate likelihood to the other. Right? So this is the same kind of setup Emtiyaz was talking about, where the likelihood is this exponential family here. Theta plays the role of the natural parameter in the likelihood, and then you've got a log partition, which is A of theta. This base measure is not going to be important, and then the prior is the conjugate to that likelihood. Right? So the sufficient statistics for theta are going to be theta and A of theta. So the log partition from the likelihood ends up being augmented into the sufficient statistics in the variational family. And under this case, and this is just a standard setup. I'm describing the notation, but this is just the conjugate. This is just the case of conjugate inference. Okay, so conjugate inference with exponential families, which I guess is the only case of conjugate inference. So in that case, the exact Bayesian update is the BONG update, and the reason is that this just generalizes what MT showed with the sample mean case, right? So if we decompose the natural parameter for the variational family into these two pieces, the piece that corresponds to theta and the piece that corresponds to A, well, this new thing, it's just a degrees of freedom kind of thing. You just get increments by one, and the data just get incremented, added into the other piece, the other half of the natural parameter. This is the Bayesian update. The Bayesian update is just addition of natural parameters, and it's also exactly what BONG does. And the reason that it's what BONG does is that if you take the gradient of the NLL, which is this term up here, the expectation of this term here, if you take the gradient of that with respect to rho, the expectation ends up being you end up with an expectation of t in there. Expectation of t is rho, and so you get rho times y comma 1. And so the gradient ends up being y comma 1. The natural gradient ends up being y comma 1.
So this is written in the VLR paper, you know that?
I would like to see where.
Oh,
because I've.
5.1.
All right.
Okay.
Yeah, well, yeah.
Because it's a theorem, so I'm wondering. This was actually written in the CVI paper in Appendix C.
In which paper?
Something in the 2017, when I originally had claimed to solve the problem.
The variation. Gotcha. Yeah, and I noticed, of course, that you basically proved this in your talk just a little while ago.
Yeah.
Okay.
I also wrote this now after 8 years. I'm still writing it.
Yeah. Okay. All right. Well. Cool.
Sorry. I have a question.
Oh, yeah.
So I was wondering why you want to go with the KL term to precedence. Does it have an advantage, or is it to return existing algorithms?
The advantage is that if you include the KL term, then what we have to do is find a minimizer of this entire loss, everything over the brace, right? And we have to find the minimum of that loss. And in order to do that, we have to go through a series of natural gradient steps until we converge. The trick here is that if we drop this out of the loss, so we're not explicitly including it in the loss, the loss term that BONG updates is just the expected NLL, this whole thing. We can't run that to convergence. If we run that to convergence, we'll overfit. We'll just fit the current observation. We'll forget everything before that. But if we run a single step, this is the trick, running a single step, we implicitly regularize.
So my question was, even with the KL term, why don't you just take a single step?
Oh, well, if we take a single, two answers. One, if we in the batch setting, if we do what BLR does, which is take this to be the prior, which is size 0, then you're going to be regularizing back towards that. And a single step's just not going to get you what you want, right? You will get this purple line, right? You'll get one step and you're just not going to get to where you want to be.
So it is like you want to adapt more quickly within a single step using the observation.
Yeah. I mean, I'll show you some, if we get to it, I'll show you some timing results. And BONG is just, a lot faster than BLR because it's a single update.
And can you instead try to apply another scaling vector to kill rather than just removing?
Scaling, well, so you just want to downweight this.
Yeah, downweight it. Usually it's supposed to do.
I'm wondering if that could do anything better. I mean, the theorem that I just showed and apparently stole from MT is that if you make that downweighting factor 0, that's the optimal thing to do, right? So we might as well just do that, go all the way to 0.
For arbitrary downweighting vector other than 0, what give you the optimal Bayesian?
That's a good question. I don't know the answer to that. That would be that could be worthwhile working out. It would, yeah, thanks. Yeah, it would presumably still be an iterative method, right? I don't think you'd have a single step update that would that includes a downweighted version of the KL that gets you where you want to be, but maybe fewer steps than weighting it fully. I'm not sure. Thanks.
And just to make sure, the implicit regularization is just the fact that we have one step. Right?
Yes, exactly. Right. Yeah, for Zoom folks, the implicit regularization is just the fact that you have only one step rather than running two conversions.
I think for the conjugate case, they coincide, right?
Yeah,
because
yeah.
the natural gradient doesn't depend on psi.
Right.
So, yeah, I think the green line is very well drawn. It looks so much better.
Right. Yeah, and so I intentionally made, they will go to different places in the non-conjugate case. And so I made them slightly different, and this is just a
I feel like the main difference is not whether the step size, as you already said it, right? I think the main difference, maybe if people don't get it, this is what I see, is the expectation of psi of t given / t minus 1 versus there as something else. Am I right?
Which part are you pointing to?
I think the main difference is this.
Oh.
Versus that. So there's no slash.
Oh.
I think that's the main difference.
Well.
No, it's not.
Not really. It's just that this t comma I minus 1 refers to each of these waypoints, right? So you reevaluate. Forget about what's in this VI loss, the script L. It's just a loss function, right? And you have to evaluate that loss function at every step along the way when you iterate. And yes, that means evaluating the expected NLL at every step along the way, and expecting the end.
I think I'm lost because I feel like the green line should be exactly the same as the first arrow in the purple line.
You're right, in fact. Yeah, you're right. And yes, and it's because of this fact here that on the first step, the KL doesn't contribute anything. And like I said, Kevin and I just realized this. We were looking at the experimental results, and we said there's something particular in the experimental results that made us realize this fact. But I'd already drawn the cartoon. Yeah. And then I thought about redoing, but what it means then is that somehow the lines are going to start off parallel, and then the purple's going to diverge and maybe come back, and then I had it curve in two ways, and it just didn't look as pretty. What's it?
I feel that the line should be here, the green line.
Well, right. Either way. Yeah, or move the green line or the purple line. It doesn't matter. Yes, they do start off in the same direction. That's absolutely right. The two algorithms start off in the same direction, but one jumps to the endpoint in one step, and the other doesn't. Yeah. Okay. So let's derive this for the Gaussian case. So if you have a Gaussian prior, written here are the natural parameters in this case, then we can derive what the BONG update is, and it exactly matches the explicit version of their RVGA update that I showed you earlier. And this derivation, you can it follows the same thing as in the Vaughan paper, the Adam paper, where you just use the chain rule and use the bond end price terms. More generally, we can apply this to a number of different variational families, rather than just the full. So Gaussian case, a full covariance Gaussian prior means that it's quadratic in the size of the model. It's you've got a theta by theta matrix. So we can trade off efficiency for expressiveness by using things like a diagonal Gaussian or things in between that I'll talk about. And we can compare different parameterizations. So here I'm doing things, I'm taking psi to be the natural parameters. Now you don't need natural parameters in order to do natural gradient descent. Those are actually distinct concepts. If you do natural gradient descent on natural parameters, you get this nice closed form update that relates to mirror descent because you're just doing the update. The natural parameter update is based on the gradient of the dual parameters, so the duality gives you some efficiency, but you can still do NGD on other parameterizations, so we consider that as well. This is sort of an overview of something I'm going to do for the next several slides, which is a variety of different methods that we can derive from this framework. Okay? So we can look at different variational families. We can look at different update rules. So BONG is NGD with this implicit regularization trick, this one-step update. And we can drop either or both of those assumptions and get a 2x2 set of algorithms. So if instead of doing the one-step update, we do the explicit regularization with an iterated update, we get this online BLR, and then we can do both, and then we can do gradient descent versions of both rather than natural gradient descent. If you do gradient descent version, well, I'll get into it, but you get all four of those algorithms. Finally, there are issues with how we get these expectations, how we compute these integrals. So as I just showed you in the general Gaussian case, the update requires these two expectations. Expectations over the belief state of the gradient and the Hessian. And those are both intractable, so we need some ways of calculating them. You can obviously just do Monte Carlo. You can sample theta from Q psi. There are linearized methods and plug-in delta methods that relate to what I talked about earlier. And then in combination with either of those, we can avoid Hessians entirely and use empirical Fisher, which is an outer product of gradients, so everything's a first order. All right, so let me go through this in a little more detail. As far as variational families go, we've looked at the full covariance Gaussian, also diagonal Gaussian, where the covariance is a diagonal. The natural parameters are shown here. And this, of course, scales linearly with the model size, whereas the full covariance requires quadratic space and sometimes cubic time, because in some algorithms, at least, you have to, some variants, you have to invert sigma, or convert between sigma inverse and sigma. As I said, we can also do moment parameterization. So we can take psi to be mu and sigma instead of the natural parameters, and look at performance of the algorithms in that case and see if there really is a benefit of using the natural parameters. I can do that with the full covariance Gaussian or the diagonal Gaussian. And then finally, the representation that actually turns out to be the most effective is this diagonal plus low rank Gaussian, which has been used in a few other papers, including one of our group recently, and was first done in BLR in the Slang algorithm, which is this paper here. Where you write the precision as a sum of a diagonal matrix and a low rank matrix, an outer product, where W is some P by R matrix, where R is some much smaller number, 10, for example, whereas P is in the millions. Okay, move on from that. As far as the update rules, like I said, we have 4 update rules. So there's BONG, which is one-step NGD just on the negative log likelihood. BLR is you iterate on the full VI loss, so you have the NLL plus the KL term, and then we can do gradient descent versions of both. So instead of doing natural gradient descent, we can do what we call BOG, which is take out the natural from BONG, you get BOG, and the online version of BBB, which was the older method that preceded BLR, where you just do GD instead of NGD. Right? So we have all 4 of these, and they're a 2x2 structure of algorithms. All right, as far as approximating these expectations, we have to compute expected gradients, expected Hessians, which I denote this way. Like I said, we can do Monte Carlo, where we just draw samples from the belief state, or we can linearize in ways. I'm going to elaborate on both of these. We can linearize the likelihood, make it a linear function of theta, and then get closed form updates. In conjunction with both of these, we can use either second order methods or first order methods, where we compute the second derivative of the full Hessian at each observation, or we can use the empirical Fisher, the outer product of first order gradients. And that leads to 4 combinations of means for approximating these lower and capital G's, expected gradient and Hessian. Monte Carlo is pretty straightforward. You just sample a bunch of theta hats from the belief state. You approximate the mean gradient as the empirical average from that sample, approximate the Hessian as the empirical average of the Hessians from that sample. Or alternatively, that's the MC Hessian approach. The thing that we call MCEF approach is you take the outer products of all the gradients from all your samples and take the average of those. And for folks who know the EF method, I'll justify it on the next slide. That turns out, when the loss is log likelihood, this turns out, the outer product of gradients turns out to be a decent approximation of the Hessian. And this has been used in VLR as well. For linearized methods, again, if we assume that the likelihood is an exponential family, not conjugate, we're in neural network land now, there's no conjugacy anymore, but we assume that what the network is outputting is some f of theta, which is the natural parameter of the likelihood. Then we also define the dual parameters, which are the expectation parameters, the expectation of the output conditioned on the natural parameters. So, and this is totally standard in machine learning, right? So, for example, if you're doing classification, your neural network is outputting the logits, which are the natural parameters of your categorical distribution. And then when you have a softmax layer that sits on top, those are the probabilities, those are the dual parameters. So softmax of the natural parameters is the dual parameters. So we can think of F as the output of one layer, and then H is just after we apply softmax. So we can do a couple of different things. We can linearize the network in terms of H, in terms of the probabilities. So we linearize H, and then we approximate the likelihood as a Gaussian, where H bar is the mean, and then we just take the conditional variance at the prior mean of theta for the variance. So I'm not saying that so well, but we define a linear Gaussian model that's based at the prior mean for theta. The other thing we can do is linearize F, linearize the natural parameters, for example, the logits, and not Gaussianize. So we can keep whatever parametric family the likelihood is, right? All we've done is taken the original likelihood and plug in F bar for F, so we've just linearized the network at that stage. And then do a plugin. So rather than integrating this expectation, well, not this expectation, but integrating the gradient and the Hessian, rather than integrating them over all of Q psi, we just plug in the mean. So these are 2 approximations that we can do, and they turn out to be equivalent. Okay, linearizing in one way and assuming a Gaussian likelihood gives you a closed form update. Linearizing in this other way and using a plugin delta function at the prior mean gives you a closed form update, and they are the same. And they look like this. This is not in terms of the update, but these are the ingredients that go into the update. Your expected gradient can be written this way. Your expected Hessian can be written this way, where capital H is the Jacobian of the network, and R is, again, the conditional variance of the output. And so that, anyway, this is just another theorem that we proved that that you can arrive at the same approximation. And this approximation is shown up in different places. For the Hessian, it's just the GGN approximation. And you can arrive at it in a couple of different ways.
I think when you do BONG, you already get it. Or is that
No, BONG does not. So what we define, no. We have 4 different versions of BONG. We have BONG with Monte Carlo and BONG with linearized, right? and then those are crossed with this Hessian versus empirical Fisher. But the Monte Carlo version of BONG, which was from a few slides ago, is this, right? None of the linearization comes in. We're doing an empirical estimate of the gradient.
Maybe I'll tell you later, actually. Maybe maybe not useful right now. Yeah.
Okay. Our previous paper, which is, the lo-fi paper, that is the linearized version, right? So that's where that comes in. Lo-fi is BONG plus the linear approximation on a DLR belief state. Right. So finally, we can do EF in the context of the linear approximation. So this is just one further approximation. So first of all, notice that the expression for the expected gradient, which here requires the Jacobian, you can write that in a Jacobian freeway. You can write it as the gradient of a scalar quantity, which is this quantity right here, which is just the imputed Gaussian likelihood. Even though the actual likelihood is not Gaussian, the thing that you get from these linear approximations turns out to be the same as the gradient of the scalar log likelihood for Gaussian. So you can compute this in a Hessian freeway. And then we can get a, Jacobian freeway. And then we can get a Jacobian free estimate of the expected Hessian by using the empirical Fisher method once again. And for folks who aren't familiar with empirical Fisher and why you would do this, why would you possibly take the outer product of gradients and call that the Hessian? It actually turns out to be the right thing to do in simplified settings like this one here. So when the model is linear, and if the model is correct, meaning that the output, the prediction coming from the model is the true expected value of the observation, then it's pretty straightforward to show that, first of all, this is just a definition, right? The expected value of y minus y hat outer product is the conditional variance of y. And if you plug that into the formula for little g and then big G, what you get is that the expected value of this quantity here, just plug it in up here, is the same thing as the exact Hessian under the linear approximation. So everything is within the world of the linear approximation of the network, but in that case, the EF gives you exactly the Hessian. And that's sort of the justification that people use more broadly for using empirical Fisher as a Hessian approximation. Which is slightly different from using it as a Fisher approximation, but here we're using it for the Hessian. So putting all that together, we get a whole space of methods where we cross the different update rules. So this is with and without NGD and with and without the implicit regularization. The different methods for approximating the integrals and the different variational families. And people have been doing a good job of interrupting me, but now I'm going to switch over to just run through a few experimental results. But if anyone else wants to say anything more about theory before I get into that. Okay, so what do I want to do here in just 5 minutes? So what we want to do so we run a bunch of experiments to compare the different methods. And we want the most important thing here is to test out the core principles that go into the BONG method, right? So there's the implicit regularization, which BONG and BOG have, but BLR and BBB don't. There's the NGD, which BONG and BLR have, but the others don't. Then comparing these linearization methods, right? So I'm not doing all 4 methods for computing the Hessian. We're doing the linearization method in the context of getting the exact Hessian. We don't need EF in that case. So it's with the Jacobian of the network and comparing that to the Monte Carlo method in conjunction with EF. Monte Carlo is more expensive. Computing the Hessian is more expensive with Monte Carlo because you have to compute the Hessian of the whole network. So we use EF there because otherwise it would just be too costly. And then finally we do comparison. Well, I'm not really going to talk about this, but the natural parameters versus the moment parameters. So those are the 4 principles that go into the method overall. We do it on a few different data sets. I'll just talk about the MNIST data set here. And we look at standard metrics, speed, computation time, right? And then misclassification and predictive likelihood. Let me not get into the other details there. So here's speed. Sorry, these graphs are maybe a little bit hard to read, but on the left, what we're doing is we're comparing with the full covariance Gaussian for our belief state for our variational family. We're comparing the 4 update rules crossed with the 3 of the 4. We just didn't implement the 4th method for approximating the integrals. And then on the right, we're doing this with the DLR variational family, and comparing the 4 update rules with just 2 of the updates. And there we go. So what you can see is that the linearized methods are a lot faster. So linearized methods are the orange here. So anything that says lin1 is linearized, right? So the orange, the purple X, and the gray box compared to, so boxes, shapes, circles, X's, boxes, and stars are the different update rules. So you can see overall, BONG and BOG, which are the one-step methods, are a lot faster than the iterated methods, BLR and BBB, and the linearized version of every method is faster than the nonlinear version of the method. And this is true in the full covariance case, and this is also, you get the same pattern qualitatively at least with the diagonal plus low rank approximation for the variational family. As far as performance goes, so here's performance on MNIST, comparing the 4 update rules crossed with 2 of the 2 main integral approximations, and this is all done with the DLR matrix, DLR matrix for the covariance. And this is, let me actually go back and tell you what the network is. So this is a CNN with 58,000 parameters. Right? That's the size that we're looking at. And we see benefits of the 3 main principles of the model. The fourth one, the fourth one I listed a moment ago, was natural parameters. That's not relevant here for this experiment. But we see the implicit methods are faster than the iterated methods. The natural gradient methods are faster than the gradient descent methods, and linearization helps. And overall, this is a win for the linear BONG, which is the lo-fi paper that we published a year ago, which is the gray line at the bottom. So you see that in terms of statistical efficiency. You also see it in terms of time efficiency. The lo-fi is faster than just about everything else as well. BOG is a little bit faster because actually, why is the gradient descent faster than the natural gradient? I don't think we had a good answer for why BOG is faster than BONG, because this is. Oh no, I do know why. Yeah, this is actually worth talking about for a second. No, stop. This DLR family, this diagonal plus low rank, it's not an exponential family. So doing natural gradient descent on the DLR representation is actually tricky. And we do the same thing that Slang did, where instead what you do is natural gradient descent in the full covariance representation. So you do the update with respect to mu and sigma, the natural parameters mu and sigma, and then you get a posterior which is of higher rank than the prior. Whatever your rank was for the prior, you're adding the new rank is adding the dimensionality of the observations, because you get an outer product for each dimension of the observation, and then you project back down using an SVD step. So that's what we do there, and that's why BONG costs a little bit more. But yeah, overall, we've got a bunch of other experimental results if anyone wants to see. But overall, what we see is that this is basically the conclusion, is that we see benefits of all 3 components of the method, and it's a nice win for a model that we published a year ago. Let me stop there. Thanks.
These are all Gaussian, right?
You mean the parametric? So these are all, every variational family we looked at was Gaussian with just different versions of the covariance. So full matrix covariance, diagonal covariance, or this DLR, diagonal plus low rank covariance. I'm not really aware of any work. I mean, it's kind of funny because we all talk, people who do VI for neural networks talk about different variational families, and there's little work, very little, that uses anything other than a Gaussian for the distribution over the parameters. I've wanted to do that kind of stuff, but if there's, yeah, I mean, I'd be interested to know of anything that people know that's been successful using a non-Gaussian variational family. Because other families, I mean, so for example, okay, yeah, so you've got one for binary networks, right? 0-1 networks. You can do a Bernoulli.
You can do scale mixture Gaussian, and you could also do like
sure.
rank stuff with. I mean, it's all there. It's just not very accessible right now. So we should. I'll tell you.
Yeah, scale mixtures, of course. Yeah, right. That relates to another, the other paper, the Wolf paper that we just did. Yeah, pretty similar.
There was a question. One last one.
I have a question, but maybe it's come from a misconception. When everything is stationary, then would your online algorithm correspond to a batch algorithm?
Yeah, that is a really important question. The answer is no, and that's because, and that's true for any Bayesian filtering method, because of the fact that you apply the variational approximation at each step. Oh, I'm sorry, I did the wrong thing. Sorry. There, okay. So, in order to get the posterior here, in a filtering setting, you take the approximate prior from the previous step and then combine that with the likelihood of the current observation. This thing, even in the absence of dynamics, this thing is an approximation because you've applied the VI approximation on prior steps. So you're doing this KL projection at every step, and rather than doing it a single time as you would in a batch setting. And moreover, the ordering will matter. So the ordering of the data will matter because you're projecting out. So presumably you have poorer representation of earlier observations, not because of any dynamics, but just because they've been subjected to more of these KL approximations.
Thank you. I have another small question.
Yeah.
So you don't have a step size in your algorithm.
Right.
Does that make sense to have one?
No, based on the first theorem that I presented, the exact right thing to do is to have an update of one. Yeah, and we have some experimental results, and it's an advantage, of course, because here's just BLR. Here's some experiments varying the learning rate for BLR, and one line here, the blue line is BONG, and then you have different performances of BLR with different learning rates. This is 1 iteration, this is 10 iterations. And with the right learning rate, BLR can perform about as well as BONG, but it's sensitive to the learning rate. So I mean, it's just a standard idea that you don't have a hyperparam that you have to tune, which is nice. Yeah.
I think it's like one pass through the data, no?
What is?
It's like in batch setting, this will be equivalent to doing one pass through the data?
I don't think it is for the reason I just said, because you're applying the KL projection repeatedly, which is not that. So one pass, if what you're saying is that one pass through the data
is one pass of Kalman filter, right? It's not, right? So in batch setting for Kalman filter, it's one pass through the Kalman. It's filtering.
Yeah, it is, right. Which is not the same as just doing a VI update on the whole batch at once, right? That's going to give you different results.
VI update on Kalman filter, one iteration.
Oh, yeah, of course. Yeah. Did you want to say something?
It's actually Newton's step.
Kalman filter is Newton.
If you do one Newton step in your objective, with like second order,
sure.
Step, you
sure.
exactly learning rate 1 and your update.
Right.
Because I mean the Hessian is basically Fisher.
Sure, right. Which you can compute in the conjugate case, but is obviously too expensive in the non-conjugate case.
Yeah, you're exactly right. This is Newton's.
Yeah. Yeah, of course. Yeah, I mean, it's yeah, those are the same thing.
We are slightly over time, sorry. So thanks again, for this presentation. And